Imagine, for a moment, the exact second when humanity simply stops. Not with catastrophe or drama, but with a quiet exhale. The last engine shuts off, the last voice fades, and in that profound stillness, something extraordinary begins. The first thing you would notice, if you were there to notice, is the sound, or rather, the absence of it. For the first time in centuries, the low hum that has vibrated through every city, every town, every highway simply ceases. That electromagnetic drone we've grown so accustomed to that we no longer hear it, gone. In its place, something older emerges. The whisper of wind through empty streets, the patter of rain on abandoned cars, the rustle of leaves that have always been there, waiting. Within hours, the natural world begins to remember its own voice. A dog barks somewhere in the suburbs, confused and alone. Birds, no longer competing with traffic noise, begin to sing at their natural volume. Their calls carry farther now, echoing through concrete canyons that once swallowed every sound. In forests at the city's edge, the deer lift their heads. They sense it, though they couldn't possibly understand it. Something has changed. At night, as the sun sets on this first day of absence, city lights would begin their slow farewell. Emergency generators in hospitals and data centers continue running, powered by fuel that will last days, perhaps weeks. Traffic lights blink meaninglessly at intersections where no one waits. Street lamps glow in orderly rows, illuminating nothing. But already some lights have failed. No one will replace the bulbs. No one will repair the circuits. By the second night, whole neighborhoods sit in darkness. By the first week, only the most robust systems remain lit. The great illuminated skylines of our world, those glowing towers that astronauts photograph from space, begin to flicker and fade. And above them, something humanity hasn't seen in generations slowly returns. Stars. At first, just the brightest ones. Venus, Jupiter, the major constellations our ancestors knew by heart. But as weeks turn to months, and the last emergency lights finally exhaust their fuel, the night sky deepens. The Milky Way, invisible to billions of humans who lived and died beneath it, stretches across the darkness like a river of ancient light. In the cities, where light pollution once created a perpetual orange haze, the heavens open up in their full, overwhelming glory. This process continues for centuries. Each decade, as more glass shatters and more metal corrodes, the light pollution that humanity scattered into the atmosphere diminishes. The sky doesn't just return to what it was before us. It becomes darker, clearer, more pristine with each passing century. Eventually, in 1,000 years, 2,000 years, the night above our abandoned cities would be darker than anything humans experienced even in prehistoric times, because the very air has cleaned itself of our industrial residue. But while the lights fade and the silence settles, something else is already in motion. Nature doesn't wait for permission. It doesn't pause to mourn. It simply continues. Within the first spring after our departure, seeds that have been waiting in the cracks of sidewalks finally get their chance. Without the constant trampling of feet, without the weekly application of herbicides, they push upward. Dandelions first, always the pioneers. Then grasses. Within a single growing season, patches of green appear in parking lots, along highway medians, anywhere the pavement has already begun to crack. The speed of this transformation would astonish us. We imagine nature as slow, patient, working on geological timescales. But that's only because we've spent so much energy pushing it back. Released from that constant pressure, nature doesn't creep forward. It surges. By the end of the first decade, vines have begun their ascent up the sides of buildings. Ivy, wisteria, kudzu in the American South, all climbing toward the light. Trees sprout from roof gutters where leaves accumulated and created pockets of soil. In just 20 years, in some cities, the streets would be barely passable, choked with vegetation that erupts from every crack, every gap, every moment of weakness in our concrete and steel. And into this emerging wilderness, the animals come. Not slowly, not tentatively, quickly. Coyotes trot down main streets within days. Deer browse in suburban gardens within weeks. In coastal cities, seabirds nest on skyscraper ledges that mimic the sea cliffs their ancestors preferred. Rats, of course, thrive at first, gorging on the stored food left in our homes and warehouses. But their population boom is temporary. Within a few years, as the food runs out, their numbers crash. And the predators that followed them, the hawks and owls and foxes, find a paradise. In less than a human lifetime, former city parks become genuine forests. Squirrels and raccoons, those adaptable survivors who learn to live alongside us, now flourish in our absence. But they're joined by others. Bears return to cities built on their former territories. In Europe, wolves pad through the ruins of Berlin and Warsaw. Mountain lions reclaim Los Angeles. These animals are not invaders. They're coming home, and they bring with them the forest itself. A bird lands on a windowsill and defecates. In that small dropping are the seeds of berries it 8 miles away. Another bird nests in a collapsed roof, its droppings carrying seeds of oak, or maple, or pine. Year after year, birds commute between the wild forests and the crumbling cities, and with each journey, they carry the forest with them. Within a century, trees that birds planted in the hearts of our greatest cities have grown tall. A crow might deposit an acorn in the gap between a parking garage's concrete levels. The acorn germinates, the oak grows, its roots breaking apart the structure that cradles it. In Central Park, trees we planted ornamentally now drop seeds that germinate freely. Their offspring march outward, down Fifth Avenue, across Times Square, a slow green army reclaiming Manhattan. But some seeds wait much longer for their moment. Inside a collapsed office building, imagine a potted plant that once sat on a desk. The pot breaks eventually, after decades of water damage and freeze-thaw cycles. The soil spills out, and in that soil, viable seeds that have waited 100 years, 200 years, finally touch moisture and light in the right combination. They germinate, pushing up through the rubble of the building that imprisoned them. A fiddle-leaf fig, an ornamental palm, growing wild in a climate they were never meant to survive, protected just enough by the microclimate of the ruins. Meanwhile, the trees we planted deliberately, the oaks and maples and plane trees of our city streets, freed from the pruning and constraints we imposed, simply continue. No longer trimmed, no longer restricted to small squares of soil, they grow as their ancestors did. Their roots break through sidewalks, their canopies spread wide. Some of these urban trees, given time, become the ancient giants of future forests. A maple planted in 1920 might live to the year 3000, its massive trunk rising from what was once a city street, its branches sheltering a forest we could never have imagined. But not every species that thrives in this new world is native. We moved species across continents for our own purposes. Ornamental plants from Asia grace gardens in America. European plants colonize Australian cities. And when we vanish, these invasive species don't politely return to their origins. They compete, they spread, they sometimes dominate. The forests that grow in our cities might be strange hybrid ecosystems, mixtures of native and foreign species creating combinations that have never existed before. Nature doesn't care about our categories. It works with what's available. Deep beneath the cities, in the parking garages and subway tunnels, a different transformation unfolds. These spaces, dark and still, become perfect habitat for creatures that shun the light. Bats, which have always lived in our cities but hidden in small numbers, discover vast underground chambers. A parking structure beneath a shopping mall becomes a nursery roost for thousands of bats. The temperature is stable, protected from winter cold. The darkness is absolute, and the entrances, now that no one closes the gates, allow easy access. Each night, these bats pour out into the ruined city above, a black cloud against the star-filled sky, feeding on the insects that now flourish unchecked. Each morning, they return to darkness, their guano accumulating on the concrete floors, creating layers that future paleontologists might study, wondering about this strange period when bats suddenly colonized underground structures in massive numbers. The lights have faded. The silence has settled. Nature has taken its first bold steps into the spaces we left behind. But this is only the beginning. The real transformation, the deep changes that will render our cities unrecognizable, those will take much, much longer. Time, after all, is something nature has in abundance. And now, finally, it is time to work undisturbed. In the beginning, the decay is so subtle you might not notice it at all. A building stands as it always has, solid and permanent against the sky. But look closer. Run your hand along the wall if you were there to do so. The paint feels different now. Chalky, loose. After just one winter, the first flakes begin to lift in the wind. Rain is the great eraser. Each droplet that strikes a painted surface carries away microscopic particles of pigment. So gradual, so gentle, that it seems like nothing at all. But rain is patient. It falls and falls year after year and never grows tired. Within a decade, the bright colors of our world begin to fade. The cheerful yellow of a school bus rusts through to orange, then brown. The bold red of a fire hydrant softens to pink, then gray. Billboards, those massive declarations of commerce and desire, lose their messages first, the inks running and fading until only ghost images remain. By the 50th year, color itself becomes rare in the ruins of our cities. Everything trends toward the same palette: gray concrete, brown rust, the green and black of growing things. The visual cacophony of human civilization, all those carefully chosen hues meant to attract and persuade and identify, washes away down gutters and storm drains, carried grain by grain back to the earth. But rain is only one force among many. Temperature is the other great destroyer, and it works through paradox. Heat expands, cold contracts. Each day, as the sun rises, every material in the city swells microscopically. Each night, as temperatures fall, everything shrinks. This endless breathing, this expansion and contraction, creates stresses in materials that were never meant to experience them without maintenance. In northern cities, the damage is particularly severe. Water seeps into cracks during autumn rains. Winter comes and that water freezes. Ice, as it forms, expands with tremendous force, can split granite. Concrete doesn't stand a chance. Each winter, the cracks grow wider. Each spring, more water penetrates deeper. The process accelerates, feeding on itself. In desert cities, the mechanism is different but equally destructive. Daytime temperatures soar, causing massive expansion. Night brings sudden cold, rapid contraction. This daily cycle, more extreme than the seasonal changes of temperate zones, fatigues materials quickly. Metal expands and contracts, loosening bolts and rivets. Glass, stressed by its frame, develops microscopic fractures that spread like spiderwebs. Within a century, no surface remains pristine. Everything is weathered, cracked, preparing for the next phase of dissolution. And into these cracks, the pioneers arrive. Moss first, almost always moss. It needs so little. Just moisture, just light, just the tiniest purchase on the surface. Spores, invisible and numberless, land everywhere. Most die, but some find the perfect conditions. A north-facing wall that stays damp, a crack that holds a grain of dust. The spore germinates. The moss begins its patient work. Moss doesn't just grow on surfaces. It actively breaks them down. It produces weak acids that dissolve stone and concrete, extracting the minerals it needs. It holds moisture against the surface, accelerating decay. Where moss grows, other organisms follow. Bacteria, fungi, tiny invertebrates, each contributing to the slow transformation of human materials back into soil. Lichen comes next, those strange dual organisms, part fungus, part algae, cooperating in a partnership older than forests. Lichen is even more aggressive than moss. It can colonize surfaces that seem impossibly hostile. Bare metal, glass, plastic. Give it a century, and lichen covers everything. The buildings become living things, green and orange and gray with biological crusts that slowly, grain by grain, consume the materials beneath. This biological weathering accelerates the work that water and temperature began. Surfaces that might have lasted millennia in a sterile environment crumble in centuries when life is actively working to unmake them. And the water never stops. Every rainstorm flows over buildings, through gutters, down walls. But now the drainage systems are failing. Leaves clog the gutters. Debris blocks the downspouts. Water pools where it was never meant to pool, finding new paths, carving new channels. A rooftop becomes a temporary pond during heavy rains. The water finds a weakness, a gap in the flashing, a crack around a vent. It flows inside, down through the building, following gravity, seeking the lowest point. Over decades, this flowing water creates something remarkable. Artificial canyons carved through our structures. A steady drip through a concrete ceiling where's a groove, then a channel, then a waterfall. Minerals in the water are deposited, creating formations that mimic the stalactites and stalagmites of natural caves. In a shopping mall, water pouring through a collapsed skylight carves a canyon through 3 floors, the smooth walls polished by centuries of flow. These water-carved structures become features of the landscape, as distinctive and beautiful as anything in the natural world. Future geologists might puzzle over them, these 2 regular formations, until they realize they're standing in what was once a building. The buildings themselves begin to fail structurally, but not all at once. Collapse comes in stages, layer by layer, each failure preparing the ground for the next. The roof goes first, almost always. Roofs are vulnerable, exposed to weather, dependent on materials that degrade quickly. Asphalt shingles last perhaps 20 years without maintenance. Flat roofs with their waterproof membranes might last 50. But eventually they all fail. When the roof goes, everything accelerates. Rain and snow fall directly onto upper floors. Wooden structures rot rapidly now. Metal corrodes. Ceilings collapse, crashing down onto floors below. This adds weight, stresses that the floors were never designed to bear. The top floor gives way, pancaking down onto the one below. That floor, stressed beyond its limits, fails in turn. For a while, this creates something unexpected: temporary cliffs. A building loses its front wall, but the back wall stands. The exposed interior, with its floors and rooms visible like a dollhouse, becomes a vertical habitat. Cliff-dwelling birds nest in what were once apartments. Vines cascade down from floor to floor. Small mammals traverse the levels, moving between ecological zones as surely as animals climbing a mountain. These partial buildings, these accidental cliffs, can stand for surprisingly long periods. The remaining walls, though stressed, find a new equilibrium. They might stand for centuries, gradually weathering, until eventually they too surrender to gravity and time. Beneath the concrete facades, the steel skeletons of our tallest buildings undergo their own transformation. Steel is strong, incredibly strong, but it's also vulnerable. It rusts. Iron oxide, that reddish-brown stain, is iron returning to its natural state, undoing the smelting and forging that created it. In dry climates, steel can persist for centuries. But in humid regions or coastal areas with salt air, the decay is rapid. The protective paint fails within decades. Water reaches the bare metal. Rust blooms like a flower, flaking away, exposing fresh metal beneath to continue the process. The massive I-beams and columns begin to weaken. Rust doesn't just stain, it expands. A steel beam can swell as rust forms, cracking the concrete around it. The rust flakes away, carrying iron back to the earth, making the beam thinner, weaker. After 300 years, a skyscraper steel frame might be so corroded that it can no longer support the building's weight. The collapse, when it comes, is sudden and total. But even as the steel rusts away, it feeds the soil around it. Iron is a nutrient necessary for plant growth. The ruins of our buildings become gardens, enriched by the very materials that once defied nature. Concrete, we thought, was nearly eternal. Roman concrete structures have lasted 2,000 years. Surely our modern concrete, engineered with precision, would last even longer. But we were wrong. Our concrete is different from Roman concrete and in some ways more vulnerable. Modern concrete is steel reinforced. The steel inside gives it strength, allows it to span great distances, and supports enormous weights. But that steel is also its weakness. When water penetrates the concrete and reaches the steel rebar inside, the steel rusts. And when steel rusts, it expands. This expansion creates tremendous pressure from within, cracking the concrete that surrounds it. The cracks allow more water in, more rust forms, more expansion occurs. The process accelerates. Within 2 centuries, most reinforced concrete structures are failing. The concrete itself might chemically last for millennia, but the steel inside destroys it from within. Chunks of concrete fall off, falling away to reveal the rusted rebar beneath. Beams crack and sag. Columns crumble. The concrete that survives longest is unreinforced, like Roman concrete or the massive foundations and dams we built. These might indeed last thousands of years, slowly dissolving in the slightly acidic rainwater, but intact. Stone, by contrast, is patient. The stone buildings of our world, the monuments and cathedrals, the courthouses built from granite and marble, these outlast everything else. Stone doesn't rust. It doesn't rot. It weathers, yes, carved by wind and rain into softer forms, but this process takes millennia. A cathedral might lose its roof after a century, its wooden trusses and lead flashing succumbing to time. But the stone walls stand. Birds nest in the arches. Trees grow in the nave, their roots finding purchase between the flagstones. After 1,000 years, 2,000, the walls still rise, though weathered and colonized by life. These stone structures become the most enduring monuments to human civilization, lasting long after our steel and concrete has returned to Earth. Near the oceans, though, nothing survives long. Salt air is the great accelerator of decay. Salt penetrates everything, drawing moisture, catalyzing corrosion, breaking down chemical bonds. Coastal cities, some of humanity's greatest metropolises, face a uniquely aggressive assault. Metal corrodes at 5 times the rate it does inland. Paint fails in years instead of decades. Concrete, penetrated by salt, degrades rapidly as the salt attacks both the concrete and the rebar within. Within a century, coastal buildings are severely compromised. Within 3 centuries, most are gone, collapsed into picturesque ruins by the sea. The salt doesn't just destroy through corrosion. It enables life. Salt-tolerant mosses and lichens colonize surfaces faster near the coast. Marine organisms, when storm surges flood lower floors, establish colonies inside buildings. Barnacles and mussels cement themselves to walls. When the water recedes, they die, but their shells remain, and the next storm brings new larvae to continue the colonization. The great coastal cities, the ports and beaches that drew humans for millennia, are erased more quickly than inland settlements. The ocean, which gave them life, now eagerly reclaims them. And in this reclamation, there's a symmetry. These buildings, after all, were made largely of materials taken from the earth. Iron or limestone, sand. The ocean and the atmosphere are simply returning them, molecule by molecule, to their origins. And so the first cracks become the first collapses. The decay that began so quietly, with flaking paint and hairline fractures, has accelerated into something unstoppable. Our cities are unmaking themselves, not through catastrophe, but through the patient, relentless work of physical and chemical forces that never sleep, never tire, and never stop. The age of slow dissolution has begun, and it will continue for centuries more. Water is the ultimate author of landscapes. Given time, it writes and rewrites the surface of the earth with a patience that makes mountains seem temporary. And now, with humanity gone, water reclaims its ancient authority over the spaces we tried to control. Our cities were never built in defiance of geography. We built them where water was, beside rivers for transportation, near coastlines for trade, along loch shores for resources. But we channeled that water, confined it, told it where it could and could not go. We paved over floodplains and built walls against tides. We buried streams in culverts and forced rivers into straight concrete channels. For a while, with constant maintenance, these systems held. But maintenance has stopped, and water, which never forgets its original paths, begins to remember. Consider a river that flows through a city center, constrained between concrete embankments. In the first years after humans vanish, nothing seems to change. The river flows where we told it to flow, contained and controlled. But during the first major flood, debris accumulates against a bridge. Trees that fell across upstream sections lodge against the pilings. Sediment builds up behind this accidental dam. The water level rises, seeking new outlets. It finds them, a crack in the embankment, stressed by decades of freeze-thaw cycles. Water under pressure exploits this weakness. The crack widens. During the next flood, water pours through, carving a new channel through streets that haven't seen flowing water in a century. The river, given this opportunity, doesn't return to its concrete prison. It widens its new channel with each flood, moving sediment, undercutting foundations, pulling down buildings that stand in its way. Within 300 years, the river has completely rewritten its course through the city. It meanders now, following the natural topography that our streets and buildings tried to ignore. The old concrete channel still exists, dry and crumbling, a monument to our temporary victory over hydrology. But the river has moved on, creating new wetlands, new oxbow lakes, new floodplains where office buildings once stood. This process repeats in every city built on a river. The Thames, the Seine, the Mississippi, the Ganges, all of them shake off their constraints and return to something closer to their ancient patterns. Not identical because the landscape has changed, but recognizable. Rivers flowing as rivers should, spreading wide during floods, narrowing during droughts, moving across their floodplains in the slow dance that shaped them over millennia. And those floodplains, which we foolishly built upon, return to their original function. The neighborhoods constructed on low-lying ground beside rivers, once protected by levees and pumps, become wetlands again. Every spring flood spreads water across these areas, depositing sediment, creating habitats for water birds and fish. The basements of homes become pools that fill and drain with the seasons. Forests grow in what were once living rooms, their roots adapted to periodic inundation. These new floodplain forests are rich ecosystems, more diverse than the agricultural land or urban development that preceded them. Beavers return, building dams that further complicate the hydrology, creating ponds and wetlands that persist through dry seasons. The landscape becomes a mosaic of water and land, constantly shifting, impossible to map with any permanence. Throughout the cities, the reservoirs we built to store drinking water undergo their own transformation. These artificial lakes, held behind concrete dams, were maintained at specific levels, their shorelines managed, their water treated. Now the treatment plants are silent. The dams, built to last, continue holding water, but everything else changes. Without chemical treatment, the water becomes truly alive. Algae bloom in the sunlight. Fish, if there were any, multiply without being harvested. Birds discover these inland seas and bring with them the eggs of aquatic plants, stuck to their feet and feathers. Within decades, the reservoirs host complex aquatic ecosystems. Water lilies spread across the surface. Reeds colonize the shallows. Herons stalk the margins. These reservoirs become permanent features of the landscape, quiet inland seas that might last thousands of years. The dams, massive concrete structures, are among the most durable things we built. They require little to continue functioning. As long as the spillways remain open, allowing excess water to escape, the dams can stand for millennia. Behind them, the reservoirs become ancient lakes, as natural seeming as any body of water, their human origin gradually forgotten by everyone except the geologists who notice the suspiciously regular dam at one end. In the hearts of cities, other water features emerge from unexpected places. Sports stadiums, those massive bowls of concrete and steel designed to hold tens of thousands of people, lose their roofs within a century or two. Rain falls unimpeded onto the fields below. The drainage systems, clogged with debris and damaged by tree roots, no longer function. Water accumulates. A football stadium becomes a pond, then a lake. The playing field, carefully maintained grass, gives way to aquatic vegetation. The stands, tiered seating rising around the central basin, become nesting sites for water birds. Turtles sun themselves on the concrete steps. Fish, arriving as eggs carried by birds from distant waters, establish populations in this strange, circular lake. Some of these stadium lakes persist for centuries, distinctive round or oval bodies of water that puzzle future observers. Why would nature create such regularly shaped lakes? Eventually, as the concrete walls crumble and collapse, the lakes either drain or merge with surrounding wetlands, losing their artificial geometry. Other water bodies, both natural and artificial, face a different fate. They fill in. Lakes and ponds persist only as long as water inputs exceed sediment inputs. Every rainstorm washes a tiny amount of soil into a lake. Rivers entering lakes carry sediment in suspension. Over time, this sediment accumulates on the bottom, making the lake shallower. In our era, we dredged lakes, removing sediment to maintain their depth. We controlled erosion in watersheds, reducing sediment loads. Without this intervention, the filling accelerates. Urban lakes, surrounded by eroding buildings and unstable soils, receive enormous sediment loads. They become shallower year by year. After 1,000 years, many urban lakes have become marshes, thick with cattails and sedges, with only narrow channels of open water. After 3,000 years, some have vanished entirely, filled in and become meadows or forests, their existence marked only by the slightly lower elevation and the water-loving plants that still grow there. But even as some water features disappear, others appear. The underground infrastructure of cities, the vast networks of pipes and tunnels we created, begins to function in unexpected ways. The subway tunnels flood, of course, within years of pumps failing. But the storm drains and sewer systems, designed to carry water away, start to work in reverse. Groundwater, no longer suppressed by constant pumping, rises. It finds the old pipes and tunnels and uses them as conduits. Water flows through these underground channels, emerging in surprising places. A drainage grate in a parking lot becomes a spring, water bubbling up year-round. A collapsed section of sewer line creates an artesian well, water under pressure shooting several feet into the air. These new springs, fed by the urban aquifer, create oases in the ruins. Vegetation clusters around them. Animals visit them to drink. Over centuries, they might erode channels, creating small streams that flow across the former city, fed entirely by groundwater flowing through our old infrastructure. The pipes themselves eventually corrode away, but by then, the springs have eroded their own natural channels and no longer need the artificial conduits. Some human structures, through accident rather than design, become permanent features of the hydrological landscape. A collapsed highway overpass falls across a stream in just the right way to form a dam. Water backs up behind it, creating a new pond. Sediment accumulates, stabilizing the structure. Trees grow from the accumulated soil, their roots holding everything in place. This accidental dam might last for centuries or even millennia, as long as any natural dam formed by a landslide or beaver activity. Behind it, a small lake becomes an established ecosystem, its origin in a highway accident long forgotten. Similarly, large buildings that collapsed in particular ways can redirect streams, create waterfalls, or form the foundations for natural dams when sediment and vegetation fill in around them. The ruins of human civilization become, quite literally, part of the geology, affecting water flow in ways that will persist far longer than the structures themselves remain recognizable. But nowhere is water's rewriting more dramatic than at the coasts. Our coastal cities, many of them built on land that is only marginally above sea level, face a particular vulnerability. Even without human-caused climate change, sea levels fluctuate naturally over geological time. But there's another factor at work: subsidence. Many coastal cities are built on sediment, on former marshland or river deltas. This sediment compacts over time, especially when groundwater is extracted. The land sinks, slowly but steadily. Without the constant construction projects that raise building foundations and strengthen seawalls, without the pumps that remove water from below-ground structures, these cities begin to sink relative to the sea. Venice, built on wooden pilings driven into soft sediment, begins its final descent within centuries. The pilings rot as the water level rises relative to the city. Buildings tilt and collapse. The famous squares become lagoons. Then, as buildings fall, become indistinguishable from the surrounding waters. Miami, built on porous limestone barely above sea level, floods during every high tide within 3 centuries. The buildings, weakened by salt air and storm damage, collapse into the rising waters. The city becomes a shallow bay studded with ruins that emerge at low tide, an artificial reef system that hosts a thriving marine ecosystem. New Orleans, much of it already below sea level when humans maintained it, floods completely within a century of pump failures. The Mississippi, freed from its levees, spreads across its ancient floodplain, and New Orleans becomes part of that plain, a scatter of ruins in a vast wetland. The ocean is not malicious in this reclamation. It simply rises and falls with the tides, probes for weaknesses, and flows into every space available to it. But its persistence is absolute. Every storm surge pushes a little further inland. Every high tide lasts a little longer. The boundaries between land and sea, which we worked so hard to define and maintain, become fuzzy, negotiable, temporary. Our artificial islands, those triumphs of engineering, succumb even faster than coastal cities. Islands created by dredging sand and rock, held in place by seawalls and constant maintenance, begin eroding the moment maintenance stops. Storm waves undercut the seawalls. Currents carry away sand. Without regular replenishment, the islands shrink year by year. Dubai's Palm Islands, massive as they are, last perhaps 3 centuries before the ocean has largely reclaimed them. The breakwaters fail first, then the waves attack the islands themselves. After 1,000 years, only scattered shoals remain, dangerous to navigation if anyone were navigating, but excellent fish habitat. Hong Kong's airport, built on a massive artificial island, suffers a similar fate. The runway becomes a reef, slowly breaking apart under wave action, the pieces gradually dispersing across the seafloor. Even our alterations to natural coastlines prove temporary. We straightened coastlines for ports and development, building jetties and breakwaters to maintain straight channels and protect harbors. These structures were never permanent, though we treated them as if they were. They required constant repair, constant reinforcement against the sea. Without that maintenance, the structures fail within centuries. And once they fail, the natural processes of coastal dynamics resume. Currents, which we briefly deflected, return to their ancient patterns. Sand and sediment, which we dredged and diverted, begin moving according to natural longshore drift. Coastlines that we made straight begin to curve again, developing the natural embayments and spits that form when waves and currents interact with the land. After 1,000 years, 2000, the coastlines begin to resemble their pre-human forms. Not identically, because sea levels might be different, because the landmasses themselves have shifted slightly, but recognizably. The natural geometry of coasts, the fractal beauty of a shoreline that develops without human interference, reasserts itself. And so water, in all its forms, rewrites the world we built. Rivers carve new channels through the ruins of our cities. Floodplains return to their ancient function. Lakes fill in or persist depending on their circumstances. Groundwater rises and creates new springs. The ocean advances, reclaiming coastal lands, eroding our artificial islands, curving our straightened shores. We tried to control water, and for a brief moment in geological time, we succeeded. But water is patient. It never stops moving, never stops working, never accepts any boundary as permanent. And in the end, as always, water wins. It doesn't win through violence or anger. It wins simply by continuing, by being what it is, by following the laws of physics that governed it long before we existed and will govern it long after every trace of our civilization has dissolved. The maps we drew are obsolete. Water is drawing new ones, and they will last until the next species comes along with their own ideas about where water should and should not flow. Time moves differently for soil. What seems solid and permanent to us, the concrete and asphalt, the steel and glass, is temporary from soil's perspective. Soil knows that everything becomes soil eventually. It simply waits and works and accumulates. The process begins with dust. Wind carries particles of clay and silt from distant places, depositing them in every crevice and corner of the ruined city. Rain washes minerals from degrading concrete and stone. Lichens and mosses, dying after their brief lives, leave behind microscopic amounts of organic matter. Leaves fall from the trees growing in the ruins, decompose, and become humus. Bird droppings and animal remains add nutrients. Year by year, grain by grain, soil accumulates on surfaces that were never meant to support it. After 1,000 years, there might be an inch of soil on a flat rooftop that hasn't yet collapsed. After 3,000 years, perhaps 6 inches. Seems so slow, but slow is the only speed that matters when you have tens of thousands of years to work with. The soil that forms isn't uniform. It's deepest in depressions where water and debris accumulate. It's shallowest on slopes and vertical surfaces. But it forms everywhere relentlessly. Even on the walls of standing buildings, a thin layer develops, enough for mosses and small ferns, which in turn add their own organic matter when they die, deepening the layer for the next generation. In some places, the process accelerates dramatically. When a building collapses, its materials break down into rubble. This rubble has gaps and spaces, perfect for soil to infiltrate. Water seeps down, carrying dissolved minerals and fine particles. Organic matter washes in during floods. Within a few centuries, the rubble pile is more soil than rubble, a raised mound covered in vegetation, with only occasional chunks of concrete or metal protruding like strange angular boulders. After 10,000 years, most of the cities are buried under soil. Not deeply necessarily, perhaps only a few feet in many places, but enough. Enough for forests. And forests do come, inevitably, in any climate where rainfall permits. The grasslands and shrublands that initially colonized the ruins are transitional states, temporary pioneers. Trees are the endpoint, the climax community, in most temperate and tropical regions. They grow slowly, yes. An oak might take a century to reach maturity. But once established, trees dominate, shading out the grasses and shrubs that came before them, creating conditions where only other trees or shade-tolerant understory plants can survive. Where Manhattan once reached toward the sky with towers of glass and steel, a new forest reaches upward now. Oak, maple, hickory, the species that covered this land before European settlement. Their roots penetrate deep into the accumulated soil, finding the rubble beneath, working their way between the broken concrete blocks that were once foundations, once walls, once monuments. The forest floor, if you were to walk through it 10,000 years hence, would seem almost natural. Ferns carpet the ground. Wildflowers bloom in spring before the canopy fully leafs out. Mushrooms push up from fallen logs. But occasionally you would notice something odd. A too-flat stone, too regular in its shape. A metal rod protruding from the earth, rusted to fragility. A scatter of bricks in a too linear pattern. The ghosts of buildings, barely visible, beneath the thriving forest. In tropical regions, the transformation is even more dramatic. Tropical forests don't just cover the ground. They explode into 3 dimensions, creating layer upon layer of vegetation. In the Amazon, in Southeast Asia, in Central Africa, where cities once imposed geometric order on the chaos of tropical growth, the rainforest returns with overwhelming vitality. The ruins provide something the natural rainforest sometimes lacks: vertical structure. The framework of a partially collapsed building becomes a scaffold for vines and epiphytes. Orchids root in every crevice. Bromeliads fill with water, creating tiny aerial pools. Ferns cascade down from what were once window frames. The forest doesn't just grow on the ground. It grows up the ruins, using them to reach toward the light. These urban rainforests might actually be more structurally complex than the natural forests nearby. They have a scaffolding of concrete and steel creating platforms at multiple heights, and the vegetation exploits every level. The result is a layered canopy so dense that the forest floor exists in perpetual twilight, even at noon. 3-toed sloths might hang from rebar protruding from a 20-story building now covered entirely in vegetation. Howler monkeys traverse what was once a shopping district, leaping between vine-covered structures. After 20,000 years, you could walk through these tropical ruins and never realize you were in a former city, unless you noticed the odd regularity in the spacing of some structures, or happen to dig down and discover the unnaturally flat layers beneath. But not every city becomes a forest. In semi-arid regions, in places where rainfall is marginal for tree growth, a different transformation occurs. The airports, those vast expanses of concrete and asphalt break down into something unexpected: grasslands. Airports were built flat, built open, specifically to prevent tall vegetation that might interfere with aircraft. Now, with the pavement cracking and breaking apart, soil accumulating in the gaps, grasses colonize these enormous open spaces. Unlike forest trees, grasses thrive on the exposure to sun and wind that these open areas provide. After 5,000 years, an airport might be an immense prairie, stretching for miles, almost perfectly flat because the pavement beneath, though broken, still influences the topography. In spring, wildflowers bloom in the millions across these grasslands. Herds of grazing animals, deer or wild horses or bison if they've returned, move across them like the great herds that once roamed natural prairies. The runways, being the most heavily reinforced portions, take the longest to break down completely. They might persist as raised linear features across the grassland, slightly elevated paths where grasses grow shorter because the soil is thinner. From above, if anyone were above to see, the outline of the airport would remain visible for tens of thousands of years, written in subtle variations in vegetation and elevation. In city centers, particularly in temperate zones, something remarkable happens in what were once shopping districts and commercial areas. These zones, with their complex mixture of materials and structures, their varying elevations and aspects, create an enormous diversity of microhabitats. Each ruined building, each collapsed structure, creates slightly different conditions of light, moisture, soil depth, and exposure. This habitat diversity translates directly into biological diversity. In a single city block, there might be dozens of different plant communities, each adapted to the specific conditions their patch provides. A north-facing collapsed wall stays moist and cool, hosting ferns and moss gardens. The south-facing side of the same ruin bakes in the sun, supporting drought-tolerant grasses and succulents. A deep pocket of soil in a collapsed basement supports a grove of trees. A thin soil layer on an elevated concrete slab hosts only shallow-rooted wildflowers. These complex, varied habitats attract an incredible array of animal species. Different insects specialize in different plant communities. Different birds hunt different insects. Predators follow prey. After 10,000 years, a square mile of ruined shopping district might host more species than a similar area of monotonous old-growth forest. Ecologists of the future, if such exist, might marvel at these biodiversity hotspots, puzzling over why they're so rich in species until they realize they're standing on the ruins of human commercial zones, where our accidental architecture created the conditions for extraordinary diversity. Among the quieter transformations, consider the cemeteries. We buried our dead in designated places, marked with stones, maintained as solemn spaces. But without maintenance, cemeteries become forests like anywhere else. Trees grow between the graves. Roots work their way around caskets, eventually breaking them open. The bones within, if not already dissolved, scatter and incorporate into the soil. The headstones, especially those of granite or marble, persist the longest. After 5,000 years, a walk through the forest might reveal these upright stones, their inscriptions weathered but sometimes still barely legible, rising from the forest floor like natural rock outcrops. Birds perch on them, vines climb them. They become part of the forest ecosystem, providing vertical surfaces in a landscape of tree trunks. Eventually, even these fall. The ground beneath them shifts as tree roots grow and die. Frost heave pushes them off-kilter. After 10,000 years, most headstones lie flat, half-buried, becoming just another kind of stone in the forest. The cemeteries have merged completely with the landscape, the dead finally returning to the earth in the most literal sense, their atoms cycling through the plants and animals of the forest growing above them. In all of this transformation, the most numerous workers, the true engineers of the new ecosystem, are the insects. We tend to think of decay as passive, but it's actually intensely active, driven by countless small organisms, with insects playing a crucial role. Termites, in tropical and subtropical regions, become the primary demolition crew for any remaining wood. They don't just eat the dead trees in the forest. They eat the wood in our structures, the framing, the furniture, the telephone poles. What would take centuries to rot naturally disappears in decades when termites are involved. Their mounds, built from earth mixed with saliva, might incorporate pieces of our civilization. A nail here, a screw there, bits of plastic embedded in the hardened structure. Ants, in their countless species, work the soil, aerating it, moving nutrients, dispersing seeds. Their colonies excavate beneath the ruins, their tunnels accelerating the breakdown of materials, providing channels for water and root growth. A single ant colony under a collapsed building might contain 1 million individuals, each one working constantly to reshape their environment. Beetles, flies, wasps, bees, butterflies, moths, each plays a role. Pollinators ensure that the colonizing plants reproduce. Decomposers break down organic matter. Predators and parasites control herbivore populations. The insect biomass in a square mile of the former city, after 10,000 years, likely exceeds the total mass of all the mammals in the same area. These insects become keystone species, their activities determining which plants can grow where, how quickly materials decompose, and how nutrients cycle through the ecosystem. Without them, the transformation would be vastly slower. With them, it proceeds at a pace that seems rapid on geological timescales. The ecological succession happening in these ruins follows paths that would puzzle classical ecologists. Traditional succession theory describes predictable stages: bare ground, pioneering annuals, perennial grasses, shrubs, early successional trees, late successional trees, climax forest. But in the ruins of cities, the sequence jumps around, takes detours, creates combinations that don't exist in natural settings. A collapsed shopping mall might have climax forest species growing in its dark, moist interior while the sunny roof hosts pioneer species, both existing simultaneously in the same structure. An invasive ornamental plant that would normally be outcompete in natural succession finds a niche in the specific conditions of a certain type of ruin and persists indefinitely. The mix of native and non-native species creates novel ecosystems that have never existed before in Earth's history. Some ecologists call these no-analog communities, assemblages of species that have never co-occurred before. In the ruins of our global cities, where we transported plants from every continent, these no-analog communities might be the norm rather than the exception. A forest in future New York might contain species from Asia, Europe, and the Americas, all coexisting in combinations never seen in any natural system, creating something entirely new. As all this organic transformation unfolds, the very physics of the city changes. Cities created what scientists called urban heat islands. All that concrete and asphalt absorbed solar radiation during the day and released it at night, making cities significantly warmer than surrounding countryside. This affected everything: local rainfall patterns, wind flow, even the migration timing of birds. But as vegetation covers the ruins, this heat island effect fades. Plants don't store heat the way pavement does. They transpire, releasing water vapor that cools the air. Forests are typically cooler than open ground. After 10,000 years, the temperature difference between former city sites and surrounding countryside disappears entirely. The local climate normalizes, returning to patterns determined by latitude, elevation, and distance from the ocean, not by human construction. The wind, too, changes its patterns. Cities created turbulent wind flows, with buildings channeling air into corridors of intense gusts, creating dead zones of still air in other locations. Weather patterns on a local scale were influenced by the presence of all these vertical structures. As the buildings collapse, as the vertical obstruction disappears, wind flows return to more natural patterns. The howling wind tunnels between skyscrapers cease to exist. The calm, protected courtyards exposed to wind. After 20,000 years, the wind blows across former city sites as it did before we built there, influenced only by the natural topography and the vegetation cover. Paradoxically, this might create windier conditions in some former cities, as the wind that was once blocked at street level now flows freely. But their natural winds, predictable, part of the normal atmospheric circulation, not the strange microclimates our buildings created. And so the forests stand where the skyscrapers stood. The grasslands spread where the runways stretched. Biodiversity flourishes in the varied habitats our ruins created. Insects, those tiny industrious engineers, rework everything at the smallest scale. Succession follows its own unusual paths, creating ecosystems that have never existed before. The heat islands cool. The wind patterns normalize. The green dominance is complete. Nature has not just reclaimed the cities. It has transformed them into something that serves nature's purposes, not ours. And this is still not the end. The forests are mature now, stable, but they're growing on top of ruins that continue to decay beneath them. The story is far from over. Time, as always, continues its work. Beneath the forests, beneath the soil, beneath the accumulated decay of thousands of years, something persists. The cities haven't vanished. They've simply moved underground. What was once above ground, reaching toward the sky, now rests below the surface, pressing down into the earth. And in this descent, they become something unexpected. Geological features, ecological niches, chemical anomalies in the planet's crust. The underground spaces we created, those voids carved deliberately beneath our cities, are among the strangest legacies we leave. Subway tunnels, parking garages, utility corridors, basements, bomb shelters, all of them represent enormous volumes of empty space beneath the surface. And while we might imagine them flooding and filling with sediment quickly, the reality is more complex and more interesting. Many of these spaces do flood, yes. Groundwater rises, rain seeps down, but not all spaces fill completely and not quickly. The largest tunnel systems, the deepest structures, might remain partially air-filled for thousands of years. Water pools at the lowest points, but air pockets persist in the higher sections, sealed off by collapsed rubble that acts as a natural dam. These partially flooded tunnel systems become extraordinary subterranean ecosystems. In the flooded sections, life adapted to perpetual darkness thrives. Blind fish, descended from aquarium species that found their way into the tunnels, navigate by sensing water movements. Eyeless crustaceans, relatives of species that already lived in groundwater, colonize the waters. Bacteria form mats on the tunnel walls, metabolizing minerals dissolved from the concrete and metal, forming the base of a food chain that exists entirely without sunlight. In the air pockets, different life persists. Bats, naturally, find these spaces perfect for roosting. But so do cave-adapted insects, spiders that evolve to hunt in total darkness, even fungi that grow in the still, humid air, drawing nutrients from the guano deposits that accumulate on the floors. These subterranean ecosystems might persist for tens of thousands of years, isolated chambers of life deep beneath the surface, until eventually the tunnels collapse entirely or fill completely with sediment. But while they exist, they represent something genuinely novel. Artificial cave systems hosting ecosystems that never existed before human intervention. Near the surface, other underground features transform in different ways. The wells we drilled, seeking groundwater for our cities, remain as vertical shafts even after their linings decay. These become conduits between surface and deep groundwater, allowing unusual exchanges. Surface water drains down them during rains. Deep groundwater sometimes rises up through them during wet seasons. After 10,000 years, with the well casings entirely corroded away, these features might function as natural springs or sinkholes, depending on the local hydrology. Animals learn these locations, visiting them to drink, just as they visited natural springs before humans existed. The well sites become gathering places, centers of activity in the landscape, their human origin forgotten but their function continuing. The subway tunnels, those linear scars cut through bedrock beneath our greatest cities, have a particular fate awaiting them. As they flood and fill with sediment, they become something paleontologists far in the future might puzzle over: long, straight fossil zones. Think about what falls or washes into a subway tunnel over millennia. Animals seeking shelter fall through collapsed openings and can't escape. Their bones accumulate in specific chambers, preserved in the fine sediment. Human artifacts, plastic and metal and glass that doesn't decompose, wash into the tunnels during floods and settle in layers. Seeds and pollen drift down, creating a record of which plants grew above at different times. After 100,000 years, when these tunnels have completely filled with sediment that has compacted and begun lithifying, they form distinctive linear geological structures. Long, straight tubes of sedimentary rock cutting through older bedrock, filled with a bizarre mixture of fossils and artifacts. Future geologists, if they exist, drilling core samples or cutting highway excavations, will encounter these features and puzzle over them. Natural processes don't create such features. Only humans did. But it's not just the voids we created that persist. The materials themselves, the stone and concrete and brick we quarried and shaped and assembled, become part of the geological record in ways we might not expect. Cities were built from Earth's crust. We took limestone and heated it to make cement. We quarried granite and marble and sandstone for building facades. We excavated clay and fired it into brick. These materials, now broken and scattered by decay, don't disappear. They're rock fundamentally, and rock persists. Over deep time, geological processes can incorporate these materials into new formations. In tectonically active regions, the broken stones of cities can be uplifted, folded, faulted, and metamorphosed. The limestone we used for construction, already metamorphosed once when we heated it to make cement, might be metamorphosed again by tectonic forces, creating bizarre hybrid rocks that have no natural analog. In a subduction zone, where one tectonic plate slides beneath another, fragments of urban rubble could be carried down into the mantle, recycled completely. In a collision zone, where continents meet and create mountains, our city's remains could be lifted up, becoming part of new mountain ranges. A future mountain climber, scaling a peak that doesn't yet exist, might place their hand on an outcrop that contains, mixed in with natural stone, fragments of concrete that were once a skyscraper's foundation. The time scale for this is immense. Millions of years, not thousands. But it will happen wherever cities were built in geologically active zones. Our materials will be incorporated into the planet's crust, mixed and remixed by forces we can barely comprehend. Even in geologically stable areas, the materials we left behind influence the landscape in unexpected ways. The trees growing in the forests above the ruins send roots down, always seeking water and nutrients. These roots are remarkably strong, capable of exerting tremendous pressure as they grow. A root encountering a crack in bedrock doesn't stop. It enters the crack, grows thicker, and forces the crack wider. This process, repeated by millions of trees over thousands of years, can fracture bedrock that seems solid. But the ruins of cities complicate this process in interesting ways. The broken concrete and rubble provide easier paths for roots to follow than solid bedrock. Roots penetrate deeper, following the artificial fractures we created with our excavations and foundations. In doing so, they extend the zone of biological weathering deeper than it would naturally reach. After 50,000 years, the bedrock beneath former cities might be more fractured, more weathered, more broken up than equivalent bedrock that never had a city above it. This affects groundwater flow, creating preferential pathways. It affects how the land erodes, creating subtle valleys where cities once stood because the fractured rock beneath erodes more easily. The landscape remembers the cities, written in the fracture patterns of the bedrock, long after every surface trace has vanished. Among the most enduring features of our civilization, ironically, are our garbage dumps. Landfills, those ignoble repositories of our waste, transform into artificial hills that might last hundreds of thousands of years. We buried incomprehensible amounts of material in landfills. Millions of tons in a single site, compressed and capped with clay and soil. This creates a raised area higher than the surrounding terrain. Initially, landfills are environmental disasters, leaching toxins, producing methane. But over thousands of years, the toxic materials break down or become inert. The methane escapes or is consumed by bacteria. What remains is simply a hill, composed of compacted materials, standing above the surrounding landscape. These artificial hills erode more slowly than natural hills might, because the compacted refuse doesn't erode easily. After 10,000 years, the surrounding natural landscape has lowered slightly due to erosion, but the landfill stands higher, more prominent than when it was fresh. Vegetation covers it completely, of course. Animals burrow into it, creating dens in the strange substrate. But the hill persists, after 100,000 years, during which the landscape around it has been reshaped by countless storms and floods. The landfill hill remains a distinctive feature. Future geologists, excavating into it, will find an incomprehensible mixture. Organic materials compressed into something resembling coal, plastics that haven't fully degraded but have become brittle and fragmentary, metals corroded but still recognizable, glass that has remained largely unchanged. It's a time capsule, but a chaotic one, mixed and crushed beyond easy interpretation. The shape of the land, its slopes and valleys, determines where water flows, where landslides occur, where sediment accumulates. And the artificial slopes we created, both deliberately and accidentally, influence these processes for thousands of years after we're gone. Highways cut through hills created artificial slopes, often steeper than natural slopes in the area. These remain, for a time, as distinctive linear scars across the landscape. But steep slopes are unstable slopes. As vegetation covers them, as their supportive structures decay, they fail. Landslides occur along these old highway cuts more frequently than on natural slopes. The moving earth buries whatever lies below, creates a jumbled, chaotic deposit. Over time, these repeated landslides smooth the too steep artificial slopes, bringing them closer to the natural angle of repose for that soil type. But while this process continues, which might take 10,000 years or more, these artificial slopes remain as zones of instability, more prone to mass wasting events than the surrounding terrain. They create opportunities for species that thrive on disturbed soil, maintain openings in the forest canopy that would otherwise close, and generally add complexity to the landscape. The weather, too, plays a role in dispersing what we built. Storms don't just weather buildings in place. They pick up pieces and carry them away. A major hurricane pushes storm surge miles inland. This surge water, receding, carries debris back toward the sea. Fragments of buildings, pieces of vehicles, chunks of pavement, all tumble in the turbulent water. The smaller pieces travel farthest. They might be deposited in salt marshes, scattered across beaches, or carried out to sea to settle on the continental shelf. Over thousands of years, countless storms redistribute city remains across broad areas. A storm in the year 5000 deposits debris 30 miles from its origin. Another storm in the year 8000 redistributes some of that debris further. Eventually, pieces of what was once a single building might be scattered across hundreds of square miles, mixed with natural sediments, impossible to associate with each other. This scattering process gradually dilutes the concentration of human materials in any one location, spreading them thin across the landscape, making them less of an anomaly and more of a background component of the sediment. But perhaps the most far-reaching dispersal mechanism is wind. We built with fine materials: concrete dust, brick powder, pulverized glass. As our structures weather and break down, they produce enormous quantities of fine particles. Wind picks up these particles and carries them. A dust storm in the ruins of Phoenix or Dubai lifts millions of tons of city dust into the atmosphere. High-altitude winds carry this dust thousands of miles. It settles slowly, over days or weeks, across deserts and oceans, forests and tundra. This urban dust is chemically distinct from natural dust. It contains unusual ratios of calcium from concrete, iron from corroded steel, trace elements from all the exotic materials we used. Over thousands of years, as billions of tons of city dust spreads across the globe, it creates a subtle but detectable chemical signal in sediments worldwide. Future geochemists, analyzing sediment cores from lake beds or ocean floors, will notice a thin layer, perhaps a few centimeters thick, that has unusual chemistry. The dates will correspond to several thousand years after human civilization ended, the period when our cities were actively breaking down and dispersing. This layer, spread across the entire planet, will be evidence of our existence as clear as any fossil. And speaking of chemistry, the soils forming on and around our ruins have compositions that would puzzle any soil scientist. Normal soil derives from weathered bedrock, with organic matter added by life. The chemical composition reflects the local geology. But soil forming on urban ruins reflects something else entirely: the bizarre mixture of materials we concentrated in our cities. Concrete releases calcium as it weathers, making nearby soil more alkaline. Corroded metal adds iron, copper, zinc, and other metals, sometimes in toxic concentrations. Brick dust, weathered paint, degraded plastics, all contribute their chemical signatures. The result is soil with nutrient ratios and pH levels that don't occur naturally. Some plants struggle in these soils. Others, particularly those that evolved on naturally unusual soils like serpentine or limestone barrens, find these urban soils tolerable and even favorable. Over tens of thousands of years, as the unusual chemistry slowly normalizes through weathering and biological processing, these soils select for certain plant species, creating distinct plant communities that wouldn't exist without the chemical legacy of our cities. After 100,000 years, the chemical anomaly is greatly reduced but still detectable. The soils are more normal, but not entirely. They contain trace elements in unusual proportions, slightly elevated levels of certain metals, pH values that are subtly off from surrounding soils. This chemical fingerprint might persist for 500,000 years or more, long after every physical trace of the city has vanished from the surface. And so the cities hide themselves, sinking below the surface, but not disappearing. They become caves and springs and fossil zones. They become part of mountains and fractured bedrock. They become artificial hills and unstable slopes. They spread as dust and debris across continents and oceans. They alter soil chemistry in ways that persist for geological ages. The cities are hidden now, but they remain. Not as monuments, not as recognizable artifacts, but as subtle alterations to the planet itself, anomalies in the rock and soil and water that speak. To those who can read such signs, of a time when beings lived here who reshaped the surface according to their own designs. The surface has forgotten them, but the depths remember, and they will continue remembering for a very, very long time. 1,000,000 years is a length of time the human mind cannot truly grasp. It's 1,000 millennia, 20,000 human generations, long enough for species to evolve into new forms, for ice ages to come and go, for rivers to carve new valleys and fill old ones. And yet, even across such spans, the cities we built leave traces. Faint traces, subtle anomalies, but traces nonetheless. The earth takes the record of our existence and preserves it, after its fashion, in ways we never intended. Consider the roads. Of all the things we built, roads covered the most area. Millions of miles of pavement, stretching across continents, connecting every city to every other. When we vanished, these roads began their slow dissolution. The pavement cracked, vegetation broke through, soil accumulated. Within thousands of years, they ceased to function as roads. Within tens of thousands of years, they were invisible at the surface. But beneath that surface, something persists. Roads were built on prepared roadbeds. We excavated, graded, compacted the soil, added gravel bases, then topped them with asphalt or concrete. This created a layer of unusually compacted material, sometimes mixed with imported gravel that's different from the local geology. After 100,000 years, with all trace of pavement gone, this compacted layer remains. It's denser than the surrounding soil, less permeable to water, more resistant to root penetration, and it preserves the shape of the roads. Long, linear features stretching across the landscape. These ghost roads affect everything above them in subtle ways. Water doesn't penetrate the compacted layer as easily, so vegetation growing above it experiences different moisture conditions than surrounding plants. The trees growing on former roads might be slightly shorter, different species, or more widely spaced. From ground level, you might not notice, but from above, the pattern would be visible. Lines of slightly different vegetation color or density, stretching for miles, following the paths our highways once took. After 500,000 years, even this trace begins to fade. The compacted soil slowly loosens as it's worked by roots and burrowing animals, by freeze-thaw cycles and chemical weathering. But in favorable conditions, particularly in areas that later get buried by sediment, the compacted layer can fossilize, hardening into a thin layer of slightly different rock composition than the layers above and below it. A geologist in the distant future, examining a cliff face or a drill core, might notice these thin, linear features cutting across the sedimentary layers. They're too straight to be natural, too extensive to be random. If many such features are found, following a regular pattern, radiating from central points like a web, the conclusion becomes inescapable. These were transportation routes of some kind, built by the intelligent species that briefly inhabited this planet. But roads don't just leave passive traces in the rock record. They also influence behavior, even long after they've vanished as physical features. Animals, always taking the path of least resistance, learn the easiest routes through a landscape. A road, even when overgrown, remains slightly flatter, slightly easier to traverse than the surrounding terrain. Deer begin using old roads as migration routes within decades of our disappearance. Their hooves were paths along these routes, keeping them clearer than surrounding areas. Predators learn to hunt along these trails. Generation after generation, the behavior reinforces itself. After 10,000 years, the road is completely invisible, but animal trails still follow its course, maintained by the behavior patterns passed down through hundreds of generations. These trails might persist for 100,000 years or more, shifting slightly as terrain changes but generally following the ancient rights of way we established. Future ecologists, if they exist, might notice that animal migration routes seem oddly straight, oddly regular. They might not understand why until someone realizes these routes correspond to the vanished road network of an ancient civilization. The shapes of our cities themselves, even after the cities have entirely vanished, continue to influence the landscape in subtle ways. Cities were built on relatively flat ground, often along rivers or coastlines. We leveled hills and filled valleys to create the flat surfaces we needed. These modified landscapes persist. A hill we leveled 5,000 years ago remains lower than the surrounding terrain. Not much lower, perhaps, but enough. This affects where water flows, where it pools, where sediment accumulates. Over hundreds of thousands of years, these subtle differences in elevation guide erosion patterns, creating valleys where we leveled hills, or causing sediment to accumulate where we created depressions. After a million years, the landscape has been significantly reshaped by erosion and deposition, but the pattern has been subtly influenced by the invisible hand of our long-vanished cities. A river's course might be slightly different than it would have been because erosion followed the path of weakness we created. A lake might exist because sediment preferentially accumulated in a depression that began as an excavation for a building foundation. The grid pattern of city streets, that most characteristic feature of urban planning, also leaves its mark. Streets were cut at right angles, dividing cities into regular blocks. This created a network of channels that guided water flow in very specific patterns. Even after the streets are gone, the slightly lower elevation where streets ran, the slightly different soil compaction, continues to guide water preferentially along those old routes. After 50,000 years, during the rainy season, water still flows along the ghost of the old grid, creating temporary streams in a pattern of right angles that never occurs naturally. Sediment is eroded from these channels and deposited in the former blocks between them. Over time, this creates a subtle topographic pattern, a checkerboard of slight depressions and slight elevations. But this pattern is fighting against natural processes that work to erase such regularities. Erosion doesn't follow straight lines naturally. Water wants to flow in dendritic patterns, branching like a tree. Gradually, over hundreds of thousands of years, the natural patterns overcome the artificial ones. The grid fades, the right angles soften into curves, the regularity dissolves into chaos. After a million years, perhaps 2 million, the grid is gone entirely. The ground has forgotten. Only random chance might create a momentary echo. 2 erosion channels crossing at nearly right angles, purely by coincidence, a brief ghost of the vanished pattern. But while surface patterns fade, the subsurface holds its secrets longer. The soil layers beneath cities are unlike any natural soil profile. Normal soil develops gradually, with clear horizons reflecting climate, vegetation, and time. Urban soil is chaos. A layer of rubble, a layer of imported fill, a pocket of ash and charcoal, a lens of pure sand from ancient construction material, all mixed together with no coherent pattern. After 100,000 years, these layers are buried under new soil and sediment. But they remain distinct. A backhoe cutting through a river eroding a bank would reveal the strange zone. Several feet of chaotic material, angular fragments in a matrix of mixed particle sizes, sometimes with intrusions of pure substances that never occur in such concentrations naturally. Future geologists encountering such layers would be confused. These don't fit any known geological process. They're not flood deposits, not landslide debris, not volcanic ash. The fragments are too mixed, too angular, too varied in composition. Only when such layers are found in the same stratigraphic position across wide areas, all corresponding to the same time period, does their origin become clear. These are the remnants of a layer of cities that once covered parts of the planet's surface. Within these urban soil layers, artifacts persist, mixed with natural sediments in combinations that would never occur otherwise. A stratum might contain pebbles of quartz, fragments of brick, microscopic shards of glass, corroded metal particles, and fossilized seeds, all jumbled together. The metal corrodes into unrecognizable lumps, but the rust remains, creating iron-rich nodules that don't match any natural formation process. The glass fragments, edges smoothed by weathering, resemble natural glass but have a different chemical composition. The brick fragments, made from fired clay, are harder than natural clay deposits and have thermal properties that reveal they were once heated to high temperatures. These strange inclusions become rare enough after being diluted by natural sediment that they're just occasional oddities. A geologist might spend a career studying sedimentary rocks and encounter such anomalies only a few times. Each time, they'd note it as unusual but might not see the pattern. Only a comprehensive survey, examining many sites from the same time period, would reveal that these oddities appear far more frequently in this particular thin layer than in any other, suggesting a global event that briefly and intensely altered sedimentation patterns. Among the most durable relics of our civilization is glass. We made enormous quantities: windows, bottles, containers, fiber optics. Glass is essentially artificial stone, silica melted and rapidly cooled. In its structure, it's similar to obsidian volcanic glass produced naturally. And like obsidian, it's very stable chemically. But glass does weather eventually. Water very slowly dissolves silica. Exposed to rain and groundwater for hundreds of thousands of years, glass fragments gradually round their edges, become pitted and frosted, and eventually break down into smaller and smaller particles. After 1 million years, most glass has been reduced to sand-sized grains. But this sand has unusual properties. Natural sand is usually quartz crystals worn from rock. Glass sand is amorphous, lacking crystal structure. Under a microscope, it looks different. Its chemistry might be slightly different too, containing elements we added to glass for color or strength. In beach sediments or riverbeds where former cities once stood, a careful analysis might reveal that 5% or 10% of the sand grains are actually weathered glass, chemically distinct from the quartz grains surrounding them. This glass sand mixes with natural sand, spreads through rivers and coastal currents, and becomes part of the sedimentary record. In a sandstone formed from beach sand 2 million years hence, glass grains might constitute a small percentage of the total. A petrologist studying that sandstone under a microscope would note the unusual amorphous grains and might wonder about their origin, never suspecting they began as windows and bottles in a vanished civilization. We also created clays, though not intentionally. When we crushed rock to make concrete aggregate, when we ground materials to powder for various industrial processes, we created enormous quantities of very fine particles. These particles, after our structures broke down, became part of the soil and sediment. Clay-sized particles behave differently than sand or silt. They're sticky, cohesive. They can be transported vast distances by water before settling out. The artificial clays we inadvertently created, formed from crushed concrete, pulverized brick, ground stone, all mixed together and spread across landscapes. After 500,000 years, these particles have been transported by water, mixed with natural clays, and deposited in lakes and oceans. But they retain subtle chemical signatures of their origin. The ratio of calcium to silicon might be unusual. Trace elements might appear in unexpected combinations. The crystal structure of the particles, formed by mechanical crushing rather than natural weathering, might be subtly different. A clay deposit formed during the era of cities, analyzed in detail, would reveal these anomalies. Not in every particle, but in a significant fraction of the population. This would mark the deposit as unusual, potentially diagnostic of a time period when intelligent beings were mechanically processing rock on a massive scale. Some materials we created have no natural analog at all. Plastics, the most obvious example, are completely synthetic. In the deep geological record, after millions of years, most plastics have degraded. But not all and not completely. Some plastics, particularly those buried in anoxic conditions where bacteria cannot thrive, might persist in fragmentary form for millions of years. These fragments, now brittled and partially decomposed, are still recognizably artificial. Their molecular structure, long chains of repeated units, doesn't occur naturally at all. Future chemists, extracting and analyzing organic compounds from sedimentary rocks, might encounter these strange molecules. They'd realize immediately that these compounds couldn't form through any known natural process. They're too regular, too specific in their structure. The only explanation is synthesis by intelligent beings. These plastic fragments would be incredibly rare, perhaps 1 per million tons of sediment. But finding even one would be significant. It would prove, beyond doubt, that technological intelligence existed on Earth during the time period when that sediment layer was deposited. Similarly, certain metals we refined and alloyed, particularly stainless steel and aluminum, have compositions that are extremely rare in nature. After millions of years of corrosion and oxidation, they're reduced to metal-rich nodules in the rock. But the ratios of metals in these nodules don't match any natural ore. The presence of chromium and nickel together in specific ratios, characteristic of stainless steel, doesn't happen in natural mineral deposits. These anomalous metal nodules become geological curiosities, rare oddities noted in scientific papers, samples stored in museums. Individually, they're just puzzling. But collectively, when many are found from the same time period worldwide, they tell a story. Something happened on Earth during this time that created materials with compositions that never occurred before and never occurred again. Perhaps the strangest legacy we leave is magnetic. Many of our materials were magnetic or became magnetized. Steel structures, exposed to Earth's magnetic field, acquired permanent magnetization aligned with the field at the time they cooled or were mechanically worked. When these structures corroded and broke down, the iron oxide rust retained some of this magnetic signature. After 1 million years, particles of this magnetized iron oxide are mixed into sediments. Most of the magnetic signal is lost through subsequent reheating or chemical alteration. But in some deposits, protected from such processes, the signal persists. Future paleomagnetists, studying the magnetic properties of ancient sediments to reconstruct Earth's magnetic field history, would notice anomalies in the layers corresponding to the city era. The magnetic signature is too strong or oriented in ways that don't match the expected field direction, or varies over distances too short to reflect natural geomagnetic variation. These magnetic anomalies would be hard to interpret. They don't fit models of geomagnetic behavior. Only when someone proposes that the anomalies come from artificial materials would the pattern make sense. The magnetized particles are concentrated in and around what were once cities, and their orientations, chaotic and varied, reflect the random orientations of corroding steel structures rather than a coherent geomagnetic field. And so Earth takes the record, incorporates it into rock and sediment, preserves it after a fashion. The roads become thin, compacted layers in the rock. The cities influence animal migration routes for 100,000 years. The urban shapes guide erosion and deposition into the distant future. The grid fades and is forgotten. Urban soil layers confuse geologists. Artifacts mix with sediment. Glass weathers into unusual sand. Artificial clays spread across the planet. Synthetic materials become rare geological oddities. Magnetic anomalies mark the sediments. It's not a clear record. It's not an easily read story. Future geologists would have to work hard to piece together what happened, to realize that all these anomalies, scattered across the globe, all dating to the same narrow slice of time, represents something extraordinary. A brief moment when intelligence arose on this planet, built a technological civilization, and then vanished, leaving only the faintest fingerprints in the rock. The Earth records everything in its way, but it's a patient recorder working on timescales where 1,000,000 years is just a moment. And it doesn't judge, doesn't preserve some things better than others because they seem important. It simply takes whatever falls into its layers and slowly transforms it all into stone. Whether that material was once a mountain or a skyscraper, a forest or a highway, makes no difference to the lithification process. We are becoming stone. Slowly, imperfectly, but inevitably. And as stone, fragments of what we built will persist far longer than they ever stood tall against the sky. The Earth is not a stable, peaceful place. It never has been. Continents drift, climates swing between extremes, volcanoes explode, ice sheets advance and retreat. On timescales of millions of years, the planet's surface is constantly being destroyed and remade. And the cities we built, now buried and fragmentary, face these forces without the protection we once provided. Some will be obliterated completely. Others, paradoxically, will be preserved by the very catastrophes that entomb them. In desert regions, our cities face a particularly complete erasure. Deserts are places of extreme weathering. Scorching heat by day, bitter cold by night, occasional violent storms, and always the wind, laden with abrasive sand. These forces break down rock quickly by geological standards. Our cities, made of processed rock, fare no better. After 10,000 years, cities in the Sahara or the Arabian Desert or the Gobi are already buried under drifting sand. The sand doesn't preserve them particularly well at first. It infiltrates every space, abrades every surface, and the temperature extremes continue to fracture materials even when buried. But over hundreds of thousands of years, a transformation occurs. The sand, piled hundreds of feet deep, compresses the layers beneath. Groundwater, when it rarely appears, deposits dissolved minerals that cement the sand grains together. The sand becomes sandstone, and anything buried in it becomes entombed in solid rock. After 1,000,000 years, the ruins of Riyadh or Phoenix exist as strange inclusions in sandstone formations. The buildings themselves have been reduced to rubble, but that rubble, now cemented in place, creates zones of different composition within the sandstone. A geologist examining such formations would notice bands of unusual material. More calcium here, more iron there, fragments of material that don't match the surrounding sandstone matrix. But the distinctive feature of desert preservation is that it erases detail while preserving mass. Individual artifacts, building features, even the overall shape of structures becomes unrecognizable. What persists is just a chemical and compositional anomaly in the rock. Evidence that something concentrated unusual materials here, but little indication of what that something was. At the opposite extreme, cities built in polar or high-altitude regions face a different fate. Cold is a remarkable preservative. Organic materials that would rot in days in warm climates can remain frozen and intact for thousands of years in permafrost. The cities built in such regions, places like Reykjavik, Anchorage, or Yakutsk, begin freezing almost immediately after heating systems fail. In the first winter, permafrost begins encroaching on areas that were kept warm by human activity. Within a century, these cities are frozen solid, locked in ice and permafrost. Everything slows down in this frozen state. Corrosion proceeds at a glacial pace, literally. Wood doesn't rot because the organisms that decompose it cannot function in frozen conditions. Even paper, even cloth, can persist for thousands of years when frozen. But permafrost is not entirely stable. It expands and contracts with temperature fluctuations, creating immense pressures. Ice crystals grow, forcing materials apart. Over tens of thousands of years, This frost heaving slowly tears frozen cities apart, fracturing buildings, mixing layers, creating chaotic jumbles of material. Then the climate shifts. Orbital variations bring warmer periods. The permafrost thaws. Suddenly, materials that were preserved frozen for 50,000 years are exposed to decay. A wooden beam, intact since the day humans left, rots away in a single summer. Paper that survived millennia, disintegrates when finally exposed to moisture and bacteria. What remains after this thaw and decay cycle is curious. Some materials remarkably well preserved, others completely gone. The pattern depends entirely on what happened to be deeply frozen versus shallowly frozen, what happened to be exposed during brief warm periods versus what remained protected. After several glacial cycles, with repeated freezing and thawing, most organic materials are gone. But some artifacts, buried deep and lucky, persist far longer than they would in temperate climates. A plastic object, frozen continuously for 1 million years, might finally emerge during a warm interglacial period, startlingly intact, an impossible survivor from an ancient world. The ice ages themselves, those periodic advances of continental glaciers, interact with city sites in interesting ways. Glaciers form where snow accumulates faster than it melts, typically in areas that are already somewhat elevated or located in regions that receive heavy snowfall. Cities, particularly older city centers, often occupy slightly elevated positions, built on hills for defense or drainage. These elevated positions, even if the elevation is just 50 or 100 feet, can influence where snow accumulates. In the early stages of a glacial period, when permanent snowfields are just beginning to form, these slight elevations can be nucleation points. The ruins of a city, even buried under soil and vegetation, create subtle topographic variations. A particularly large former building, its foundation creating a raised area, might be just high enough that snow accumulating on it doesn't fully melt in summer. Year after year, the snow accumulates. Pressure transforms it to ice. A small glacier forms. After 10,000 years, as the glacial period intensifies, this initial nucleation has expanded. The glacier that began over a city ruin is now miles across, flowing outward, grinding the landscape beneath it. Ironically, the city itself might be protected under the center of the glacier, where the ice doesn't flow much and erosion is minimal. Meanwhile, the surrounding landscape is scoured down to bedrock. When the glacier finally retreats, 50,000 years later, the area where the city once stood might be slightly higher than the surroundings, protected by its position under the glacier's stable center, while everything around it was ground away. Cities built near volcanoes face the most spectacular fate. Volcanoes are dangerous, obviously, which is why we built near them despite the risk. The soil is fertile, enriched by volcanic ash. When we vanish, the cities near volcanoes simply wait. The volcanoes don't care whether humans are present or absent. They erupt on their own schedule. An eruption 5,000 years after humans vanish buries a city in volcanic ash. Unlike the gradual burial by soil or sand, this is sudden and complete. The ash falls, sometimes dozens of feet deep, in a matter of hours. Everything is entombed exactly as it was, frozen in time by the volcanic blanket. Volcanic ash is extremely fine-grained and, when it compacts and weathers, becomes impermeable. It seals off whatever it buries from air and water. In these anaerobic conditions, preservation is excellent. Organic materials carbonize but don't fully decompose. Wood becomes charcoal but retains its structure. Even materials like paper can survive in recognizable form, though fragile. After 1 million years, the volcanic ash has transformed into tuff, a soft volcanic rock. Buried within this tuff are the compressed remains of the city, flattened and distorted by the weight of rock above, but preserved in remarkable detail. Buildings are crushed to a fraction of their original height, but the layout remains visible. Streets can still be traced. Individual rooms, though collapsed, maintain their boundaries. If future archaeologists excavate into such deposits, they would find something like Pompeii, but on a massive scale. An entire modern city, frozen at the moment of its burial, though that moment came thousands of years after humanity itself vanished. Among the stranger legacies of our civilization are the locations of power plants. Nuclear plants, coal plants, geothermal plants, all concentrated enormous energy in small areas. Even millions of years later, some of these sites retain subtle traces of that energy. Nuclear plant sites are the most obvious. The radioactive materials we concentrated there have half-lives varying from decades to millions of years. The shortest-lived isotopes decay quickly, within thousands of years. But isotopes like plutonium-239, with a half-life of 24,000 years, persist for hundreds of thousands of years. Uranium-238, with a half-life of 4.5 billion years, will persist essentially forever. After 1 million years, most of the shorter-lived isotopes are gone, but the uranium remains, concentrated in ways that never occur naturally. Natural uranium deposits are rare and form only under specific geological conditions. The uranium at power plant sites doesn't match these conditions. It's too pure, too concentrated, in the wrong geological setting. A future geologist detecting unusual radioactivity at such a site would analyze the isotopic ratios and find something puzzling. This uranium has been enriched, processed to increase the concentration of certain isotopes. This only happens in nuclear reactors, nowhere in nature. The conclusion would be inescapable. Intelligent beings once manipulated atomic nuclei at this location. The coal and oil power plants leave different traces. They concentrated and burned fossil fuels, releasing carbon dioxide. But they also left behind ash, enormous quantities of coal ash containing heavy metals and unusual chemical compounds. After 1 million years, this ash is dispersed and buried, but the chemical signature persists in the sediments. Elevated levels of mercury, arsenic, selenium, in concentrations and combinations that don't occur naturally. Even the geothermal plants leave marks. They circulated hot fluids through pipes and equipment, depositing minerals from those fluids. After millions of years, these mineral deposits, with their distinctive chemical signatures, remain as anomalies in the rock. Our industrial civilization also left a legacy in the atmosphere that takes hundreds of thousands of years to fully dissipate. We released sulfur and nitrogen oxides in enormous quantities. These formed acids in the atmosphere, creating acid rain that affected entire regions. The acid rain stopped quickly after we vanished, within decades, but its effects on the landscape persisted far longer. Acid rain leached nutrients from soil, altered soil chemistry, killed sensitive species, and etched exposed rock surfaces. After 100,000 years, the soil has largely recovered through natural weathering and the accumulation of new organic matter. But subtle signatures remain. The bedrock surfaces that were exposed during the era of acid rain show distinctive patterns of weathering, slightly different from surfaces that were covered or that weathered in different chemical conditions. Chemical analysis of sediment cores from lakes reveal layers, corresponding to the industrial era, with unusual chemistry, lower pH, elevated sulfate levels, changes in the types and abundances of diatoms and other organisms that reflect acidic conditions. These layers are thin, representing perhaps 2 or 3 centuries of industrial activity, but they're distinctive and widespread. The rivers we altered, the dams we built, the channels we dug, all influenced water flow in ways that take millions of years to fully normalize. When the dams fail, which they eventually do, the process isn't instantaneous. A large concrete dam might stand for 100,000 years before it finally collapses. When it does collapse, the lake behind it drains. But the sediments that accumulated in that lake, potentially 50,000 years worth of sediments, remain. They form a thick deposit of fine-grained material in what was the lake bed, completely different from the coarse stream deposits that should exist there naturally. The river, newly freed, cuts through these lake deposits, but slowly. Fine-grained sediments erode more slowly than gravel. It might take 500,000 years for the river to completely erode through the old lake deposits and reestablish a natural channel. Meanwhile, the channels we dug, particularly large ones like the Panama Canal or the Suez Canal, persist as topographic features for millions of years. Even after they've filled with sediment, they remain as linear valleys, slightly lower than the surrounding terrain, influencing drainage patterns. After 5 million years, the continents have drifted slightly. Sea levels have fluctuated wildly with multiple ice ages, and the landscape has been dramatically reshaped. But careful analysis might still reveal faint traces of the old artificial channels, visible as linear trends in sediment patterns or vegetation. One of the most significant impacts we had on the planet was altering the carbon cycle. We took carbon that was locked in fossil fuels, carbon that had been buried for hundreds of millions of years, and released it back into the atmosphere. This carbon then cycles through the atmosphere, oceans, and biosphere, gradually being reabsorbed. Plants take up the carbon through photosynthesis. When they die and are buried, some of that carbon is sequestered. Marine organisms incorporate carbon into their shells, which eventually become limestone. Over hundreds of thousands of years, the excess carbon we released is gradually removed from the active carbon cycle and locked back into rock. After 1 million years, much of the carbon we released is locked in new limestone formations. In coal seams formed from post-human forests, in organic-rich shales deposited in ocean basins. These formations are chemically indistinguishable from older similar formations, with one exception: their isotopic signature. The carbon from fossil fuels has a distinctive isotopic ratio, slightly depleted in carbon-13 compared to atmospheric carbon. This signature persists through the carbon cycle. Limestone formed from carbon that cycled through the atmosphere during our industrial era has a slightly different isotopic ratio than limestone formed before or after. A geochemist, analyzing carbon isotopes in sedimentary rocks, would notice a brief period, lasting perhaps 1 million years, when carbon isotopes in all types of rocks show unusual ratios. This would indicate a massive, rapid release of isotopically light carbon, followed by its gradual reabsorption. The only known mechanism for such an event is the burning of fossil fuels by an industrial civilization. Finally, in certain geological settings, our cities might be preserved in ways that seem almost miraculous. In regions where evaporite minerals form, where ancient seas leave behind deposits of salt, gypsum, and other minerals, the conditions exist for exceptional preservation. Imagine a city built near such an evaporite basin. After the city is abandoned, climate shifts bring more arid conditions. The basin begins accumulating new evaporite deposits. Over thousands of years, layers of salt and gypsum bury the city ruins. Salt is remarkable as a preservative. It's impermeable to water, preventing decay. It's toxic to most bacteria, preventing decomposition. Objects buried in salt can remain intact for millions of years. After 10 million years, plate tectonics might uplift this evaporite formation. Erosion begins exposing it. A mining operation or natural erosion cuts into the salt deposit. And there, embedded in crystalline salt, are the compressed remains of buildings, vehicles, perhaps even recognizable artifacts, preserved in stunning detail. This is how we find insects from 50 million years ago, perfectly preserved in amber. Our cities, in the right circumstances, might be preserved similarly in evaporite minerals, time capsules of incomparable fidelity, waiting in the rock for someone to eventually find them. And so the extreme forces of Earth work on our remains. Deserts bury and compress. Ice freezes and preserves, then thaws and destroys. Glaciers grind and protect. Volcanoes entomb and seal. Radioactivity lingers. Acid rain's effects fade slowly. Rivers normalize over eons. Carbon cycles and locks away. Salt and minerals encapsulate and preserve. We think of Earth as destroying evidence of our existence, and mostly it does. But in some places, under some conditions, for some materials, Earth does the opposite. It preserves, protects, and holds in trust the evidence of what we built and what we were. Not consciously, not deliberately, but through the same processes that preserve dinosaur bones and ancient forests. We are becoming fossils, and like all fossils, we will be rare, scattered, fragmentary. But some traces will persist, locked in stone, waiting across the vast expanse of time for a mind intelligent enough to find them and wonder what they mean. Deep time has a way of making everything seem small. 1,000,000 years becomes a baseline, a brief moment. 10 million years passes like a season. On these timescales, the cities we built are not monuments but blips, brief disruptions in the planet's long story. And yet, even as they fade to near nothingness, they continue to influence life itself in subtle, unexpected ways. Consider the populations of organisms that lived in our cities. Rats, pigeons, cockroaches, certain plants, bacteria adapted to urban environments. When we vanished, most of these populations either died out or merged back into their wild relatives. But not immediately. For thousands of years, some populations remained isolated in the ruins of specific cities, separated from other populations of their species by hundreds or thousands of miles. Isolation leads to divergence. Evolution works differently on isolated populations. Random mutations that would be diluted in a large interbreeding population can become fixed in a small, isolated one. Natural selection acts on whatever variations are present, pushing the population to adapt to local conditions. The rats of New York, isolated from the rats of Philadelphia for 10,000 years, begin to diverge. Physical differences emerge first: size, coat color, ear shape, then behavioral differences, mating calls, foraging strategies, social structures. After 100,000 years, they're recognizably different subspecies. After 1,000,000 years, they might be different species entirely, unable to interbreed even if brought together. These differentiated populations are frozen genetic time capsules, preserving information about their founding populations, about the evolutionary pressures of urban life, about the particular conditions of specific city sites. A future evolutionary biologist, studying the genetic relationships between rat populations across a continent, would notice something odd. Clusters of closely related populations corresponding to where ancient cities once stood, separated by populations that are more distantly related. The pattern would look like islands of genetic similarity in a sea of diversity, and that's essentially what they are. Evolutionary islands, created by the temporary isolation our cities imposed. But the cities didn't just isolate populations. They also created unique selection pressures that pushed evolution in specific directions. Urban environments were hotter, drier, more alkaline in soil chemistry, with different food sources and different predators than surrounding areas. Species that colonized cities adapted to these conditions. After thousands of generations, the descendants of those urban colonizers are better suited to the specific conditions city ruins provide than their rural relatives are. Even after 100,000 years, when the ruins are heavily degraded, some of those adaptations persist. A tree species that evolved increased tolerance to alkaline soil in urban environments continues to thrive in the slightly alkaline soils that city ruins produce. Its rural relatives, encountering these soils, grow poorly. Over time, the urban-adapted lineage expands, occupying the ecological niche created by altered soil chemistry, while the rural lineage remains in unaltered areas. After 1,000,000 years, These might be recognized as separate species, distinguished by their soil preferences. The odd part is that one species' preferred habitat seems artificial, existing only in scattered locations that correspond to former human settlements. The evolutionary legacy of our cities persists in the adaptations of species that learn to live in them. Not all areas heal at the same rate. The industrial zones of cities, where we concentrated our manufacturing, chemical processing, and waste treatment, left behind chemical contamination that persists far longer than the structures themselves. Heavy metals like lead, mercury, and cadmium don't break down. They're elements, and elements don't decay chemically. They can only be diluted, dispersed, or locked into chemical forms that are less bioavailable. This process takes hundreds of thousands of years. After 50,000 years, a former industrial site might still have soil with lead concentrations 100 times higher than background levels. Most plants struggle in such soil, but some species, through evolutionary adaptation, develop tolerance. They evolved mechanisms to sequester heavy metals in their tissues without being poisoned, or to exclude metals from their roots, or to live with lower metabolic efficiency in contaminated conditions. These metal-tolerant species become the dominant vegetation in former industrial zones. They form distinct communities, as different from surrounding forests as alpine vegetation is from lowland forests. After 1 million years, these heavy metal communities might still exist, oases of strange vegetation occupying zones of contaminated soil that correspond exactly to where humans once built factories. The contamination slowly disperses through erosion and groundwater transport, diluting over time. After 10 million years, it's mostly gone, spread so thin across the landscape that it no longer affects biology. But for that entire 10 million years, the industrial zones remained distinct, healing more slowly than the rest of the cities, marked by their unusual vegetation and the stunted growth of species not adapted to heavy metals. Water, the eternal sculptor, continues its patient work. Rain falls on the ruins year after year, millennium after millennium. The erosion patterns established in the first thousands of years continue, but they soften, becoming more natural looking. The right-angle corners of buildings, the straight lines of streets, all these erode preferentially. Corners round off. Straight channels develop meanders as water seeks the path of least resistance. After 100,000 years, the angular geometry of human construction has been smoothed into gentle curves. Rainfall patterns themselves are affected by the ruins in early stages, when large structures still stand partially. These create rain shadows and wind patterns that influence where rain falls. But as the structures collapse completely, these effects disappear. After 500,000 years, rainfall patterns in former city locations are indistinguishable from patterns in undisturbed areas. The sediment load in rivers draining former cities remains slightly elevated for hundreds of thousands of years, as the ruins continue providing easily eroded material. But this too normalizes eventually. The ruins are buried, stabilized by vegetation, or completely eroded away. The rivers carry only natural sediment, as they did before cities existed. On the longest timescales, when continents themselves are drifting apart and coming together, when ocean basins are opening and closing, the materials from our cities get caught up in these movements. Fragments of urban rubble, sediments containing city-derived particles, all of this becomes part of the moving crustal plates. When a continent rifts apart, creating a new ocean basin, the sediments along the rift margins might contain traces of former cities. These sediments get carried along as the ocean spreads, eventually reaching the far side of the ocean basin, thousands of miles from their origin. When continents collide, subduction zones consume oceanic crust, pulling sediments down into the mantle. But some sediments escape subduction, scraped off onto the edge of the continent, becoming part of mountain ranges. The Himalayas, formed by India colliding with Asia, contains sediments that originated hundreds of millions of years ago on the floor of the ancient Tethys Ocean. In the same way, future mountain ranges, forming tens or hundreds of millions of years hence, might incorporate sediments that contain traces of our cities. A future mountain climber, standing on a peak that doesn't yet exist, might be standing on rock that contains, somewhere in its mineral matrix, a molecule that was once part of a building, carried across an ocean that has since closed, uplifted into a mountain by continental collision. Our cities, quite literally, will help seed new continents and build new mountains, their materials dispersed and incorporated into the planet's long geological dance. As millions of years pass and erosion removes material from the surface, the density variations created by buried city remains can become measurable as subtle gravity anomalies. Concrete foundations, denser than surrounding soil, create tiny variations in gravitational pull. Voids in subway systems, if they haven't completely collapsed, create areas of slightly lower density. These variations are minuscule, detectable only with sensitive instruments. After 10 million years, when all surface traces are gone, when even the geological anomalies in soil layers are becoming obscure, these gravity anomalies might be among the last detectable traces of where cities once stood. A future civilization, if one arises, mapping the gravitational field of Earth in high resolution, might notice patterns. Slight increases in gravity arranged in network patterns, corresponding to where dense materials were once concentrated in building foundations. Slight decreases in gravity forming linear features, corresponding to buried tunnel systems. These patterns would be puzzling, too regular to be natural geological features, but too degraded and ancient to be obviously artificial. Only correlation with other evidence, chemical anomalies in sediments, isotopic signatures, magnetic variations, would reveal their true nature. Eventually, even the subsurface traces fade. Tunnels collapse completely, filled with sediment indistinguishable from surrounding material. Foundations, fragmented and dispersed by tectonic activity and groundwater flow, lose their coherent structure. The gravity anomalies disappear. After 50 million years, perhaps 100 million, the last physical traces of our cities exist only as chemical and isotopic anomalies distributed through sedimentary layers, and even these are becoming obscure, diluted by mixing with vast volumes of naturally formed sediments. The cities have become geological footnotes, brief, unusual episodes recorded in rock layers so thin that they can barely be distinguished, so chemically subtle that only the most detailed analysis can detect them. In the grand narrative of Earth's history, a narrative spanning 4.5 billion years, our cities occupy a moment. A few thousand years of existence, a few million years of detectable aftereffects. In a timeline where each page represents a million years, our civilization and its urban legacy occupy a single line, easily overlooked. Future geologists, if they exist and if they find these traces, would note them with interest but not astonishment. Unusual chemical signatures in Anthropocene strata. Evidence of an industrial civilization. Existed briefly, vanished, left minimal trace. Next topic. Earth has seen mass extinctions that killed 90% of species. It has seen continents split apart and reassemble. It has frozen nearly solid and heated to tropical conditions at the poles. Against that backdrop, a brief period of urbanization barely registers. It's notable, yes, but not unique. Just another event in the long, strange, violent, beautiful history of a planet covered in life. And eventually, inevitably, the traces become so subtle, so dispersed, so mixed with natural materials that they effectively vanish. After 200 million years, perhaps less, perhaps more depending on geological activity, there is no longer any meaningful distinction between the ground where cities once stood and ground that was never urbanized. Both have been weathered, eroded, buried, uplifted, metamorphosed, and eroded again. The materials have mixed thoroughly. The chemical signatures have been diluted beyond detection. The isotopic anomalies have been overwhelmed by the signal from natural processes. The ground is just ground again, ordinary, natural, indifferent. A forest grows there, or a desert spreads, or an ocean covers it, and nothing about the rocks beneath suggests that intelligent beings once lived there. The concept of a city, that idea that was so central to human civilization, that represented our ultimate imposition of order on nature, that concept has vanished from physical reality. It exists nowhere on Earth. No structure hints at it. No material anomaly preserves it. No geological feature suggests it. If memory were a physical thing, Earth would have forgotten. The planet has no memory, only records, and the records are now too faint to read. The cities have become ordinary ground, and the very idea of a city has been erased from the physical world as completely as if it never existed. This is not tragedy. It's simply time. Time doing what it always does. Flowing forward, changing everything, erasing the temporary, preserving only the occasional lucky fragment. We built cities thinking they would last, and by human standards, some did, for centuries or even millennia. But Earth operates on different standards, standards where 1,000,000 years is a reasonable unit of measurement. By those standards, our cities were snowflakes, intricate and beautiful and remarkably complex, but ultimately temporary, melting back into the water from which they were formed. The atoms that made them still exist, scattered and recombined into new forms. The energy we invested in building them dissipated long ago as waste heat. What remains is life, continuing its ancient patterns, evolving, adapting, filling niches, going extinct, being replaced. The ecosystems growing on former city sites are no longer influenced by those sites in any meaningful way. They're just ecosystems, as natural and unremarkable as any other, shaped by climate and geology and the interactions between species, not by the ghost of human presence. And perhaps that's the final fate of all civilizations, all works, all monuments. Not destruction but dissolution, not erasure but incorporation, not disappearance but transformation into something so different that the original form becomes irrelevant, meaningless, forgotten. The cities have returned to the Earth, and the Earth, patient and indifferent as always, continues its slow dance through the cosmos, covered in life, marked by geology, shaped by physics, remembering nothing, preserving little, continuing always. There is a moment, somewhere in the deep future, when the last trace of our cities finally vanishes. Not a dramatic moment, not marked by any event, just a quiet passing, unnoticed and unnoted, when the final chemical signature dissipates, when the last anomalous particle settles into complete ordinariness, when Earth's geological processes finish digesting the strange meal we fed them. After that moment, it's as if we never built anything at all. Consider the scale of time involved. Humans, as a species, have existed for perhaps 300,000 years. We've built cities for maybe 10,000 of those years. The cities as we know them, the sprawling metropolitan centers of steel and glass, have existed for less than 200 years in their full expression. 200 years of existence, perhaps 10 million years of detectable trace. On a planet that is 4.5 billion years old and will likely remain habitable for another billion years at least. Do mathematics. The period when our cities detectably affected the planet represents 0.2% of Earth's history to date. A rounding error, a statistical noise. If Earth's history were compressed into a single year, our cities would exist for about 8 hours and leave traces detectable for another 3 weeks. Then silence for the remaining 11 months. This is what brief means on geological scales. We feel permanent because a human lifetime is measured in decades. A city that stands for centuries seems eternal to us. But to Earth, we are a lightning flash, brilliant for an instant, then gone, leaving only the faintest afterglow that itself fades quickly. And the cruel truth, if it can be called cruel, is that this afterglow is indistinguishable from countless other afterglows Earth has experienced. Species have come and gone. Forests have covered the planet and been replaced by other ecosystems. Mountain ranges have risen and been worn to nothing. Oceans have opened and closed. From a sufficient distance, from a sufficient timescale, there is no meaningful difference between time when cities existed and time when they didn't. Both are just time. Earth spinning, continents drifting, life evolving. The sun is shining, rain falling. It's all the same process, the same vast planetary system functioning according to the laws of chemistry and physics, indifferent to the temporary forms it produces. Urban time becomes indistinguishable from natural time. The million years when city traces were detectable looks in the rock record like any other million years. Sediments were deposited. Species evolved and went extinct. Climates fluctuated. Nothing special happened, really, just the ordinary functioning of a living planet. We made so much noise. The roar of cities could be heard for miles. The electromagnetic spectrum was filled with our signals. The seismic monitors recorded the constant vibration of traffic and industry. The planet hummed with human activity. And then it stopped. Within a year of our absence, the noise was gone. Within a century, the vibrations ceased. Within a millennium, every sound wave we ever produced had dissipated. Its energy converted to heat, spreading out into the infinite cold of space. Sound waves don't preserve. They travel until they don't, absorbed by air and water and rock, their energy scattered and lost. Every word ever spoken, every song ever sung, every scream and laugh and whisper, all of it is gone, transformed into imperceptible increases in the ambient temperature of the universe. The silence that followed our noise is not just silence. It's erasure, complete and absolute. No recording exists except the ones we made, and those recordings, stored on materials that decay, are themselves silent now, the patterns that held music and voice degraded into randomness. Earth has forgotten every sound we ever made. Not because it chose to forget, but because sound, by its nature, cannot be remembered except by beings who choose to remember it. The atmosphere, that thin shell of gas surrounding the planet, bore the chemical signature of our industry for thousands of years. Excess carbon dioxide, methane, industrial pollutants, particulates, all of these marked the air as altered, different from natural composition. But atmospheres are dynamic systems, constantly mixing, constantly interacting with the ocean and biosphere. The carbon dioxide we released was gradually absorbed by the ocean's weathering of rocks and photosynthesis. The methane broke down under ultraviolet light. The pollutants settled out or reacted away. The particulates rained down and washed into the sea. After 100,000 years, the atmosphere's composition returned to what it would have been without us. Not exactly the same, because nothing is ever exactly the same, but within the range of natural variation. A detailed analysis might reveal subtle anomalies in isotopic ratios, but these fade too, mixed and diluted by ongoing atmospheric processes. After 1 million years, the air is just air again, ordinary and unremarkable. A deep breath of that air would taste no different than a breath taken 1 million years before humans existed. The atmosphere has cleansed itself, not deliberately, but simply by continuing to function as atmospheres do, cycling elements, mixing gases, responding to the energy of the sun. We felt things about our cities. Love sometimes, pride, often frustration, sometimes despair. These emotions were real and powerful, shaping our lives and decisions. We invested our cities with meaning, saw them as expressions of culture and aspiration, feared their loss, mourned their decay. But Earth feels nothing, cannot. It's a planet, a collection of rock and water and air and life, operating according to physical laws. It has no consciousness, no emotion, no preference for one state over another. It doesn't care that we built cities. It doesn't care that they're gone. This isn't cruelty or indifference in any moral sense. It's simply the nature of reality. Planets don't have feelings. They don't register emotional imprints. They can't be wounded psychologically or comforted spiritually. They just exist, massive and complex, following the laws of physics and chemistry, producing effects but assigning them no meaning. Our cities were meaningful to us, profoundly so, but that meaning was ours alone, existing only in our minds. When we vanished, the meaning vanished with us, completely and instantly. The structures remained for a time, but they were just structures, just matter, no more meaningful than a boulder or a tree stump. Earth continued, exactly as it would have continued regardless, unaware that anything significant had ended because it was never aware that anything significant had begun. The forests that grow over our buried cities, tens of millions of years hence, have no knowledge of what lies beneath them. The trees send roots down through soil that was once rubble, finding water and nutrients, completely unconcerned with the origin of the ground they grow in. An oak tree doesn't know it's growing above what was once a parking garage. The squirrels in its branches don't know the nuts they bury are cached in soil enriched by corroded metal. The fungi in the soil, breaking down the oak's leaves into humus, don't know that some of the minerals they're processing originally came from concrete. There is no memory in nature, not in this sense. Individual organisms might remember within their lifetimes. Species carry evolutionary memory in their genes. But ecosystems have no memory. They simply exist in the present, each organism doing what it does, the whole system functioning, completely unaware of its own history. This is not tragic. It's not even sad. It's just the way life works. Life is relentlessly present-focused. It responds to current conditions, not historical ones. The past influences the present only through its physical effects, never through memory or sentiment. The forests don't remember cities. They can't. They're just forests doing what forests do, and the fact that they happen to be growing where cities once stood is, to them, irrelevant. And yet, paradoxically, some urban locations might become sacred to future life, not through memory but through function. A former reservoir, maintained as a lake by an ancient concrete dam, becomes a crucial watering hole for migrating animals. Herds gather there every year, following routes their ancestors learned. Predators wait in ambush. The lake shapes their lives. Is it sacred? That depends on how we define the word. To the animals, it's essential, vital, a center around which their seasonal movements revolve. They don't know it was built by humans. They don't care. It's simply part of their world, as fundamental as the sun and rain. In this sense, yes, it's sacred. Sacred meaning important, central, life-giving. Human origin is irrelevant. The lake serves its purpose regardless of how it formed. Other sites might develop similar significance. A former landfill, now a hill, becomes a territorial marker for predators, a high point from which to survey the land. Birds nest there preferentially, drawn by the elevation. Over millions of years, this hill influences the distribution of species across the landscape. A straight section of former highway, now just an unusually flat valley, becomes a migration corridor. Animals learn it's easier to travel there. The behavior reinforces itself over countless generations. These places are sacred through function, through the role they play in life's patterns, not through any understanding of their history. And perhaps that's the truest form of legacy. Not to be remembered, but to continue being useful, to remain part of the world's functioning even when all knowledge of your origin is lost. When we think of restoration, we imagine nature returning to a previous state, rewinding to what existed before human impact. But that's not what happens. Nature doesn't restore, can't. Time only moves forward. Every moment is new, different from all moments before it. What grows in the ruins of our cities isn't a restoration of pre-human ecosystems. It's something genuinely new. Species that didn't coexist before are mixed together. Evolutionary changes shaped by urban environments persist. Chemical alterations to soil create novel conditions. The climate itself has changed. The result is ecosystems that have never existed before. They're not degraded versions of natural ecosystems. They're not damaged or inferior. They're just different, new, novel. Ecosystems that work, that function, that support life, but that are unlike anything that came before. Nature doesn't look backward. Can't. It only moves forward, adapting to whatever conditions exist, creating new forms, new relationships, new balances. The past is gone, irretrievable. The future is unknowable. There is only the present, constantly unfolding, constantly new. The forests that eventually cover our cities are not restorations. They're innovations, and in their own way, they're as remarkable as anything that existed before, because they represent life doing what it always does. Persisting, adapting, filling every available niche, turning obstacles into opportunities, creating order from chaos. If there were a ceremony marking nature's return, it would be quiet, unremarkable. Just another spring when seeds germinate and leaves unfurl and insects emerge and birds sing. It would look exactly like every other spring that came before and every spring that comes after. There is no moment of completion, no finishing line, no achievement unlocked. Nature doesn't complete its return because nature never left. It was always there, always waiting, always working, even while we built our cities on top of it. What we think of as nature's absence was just nature's temporary constraint. We suppressed it in certain locations, pushed it back, held it down. But it never stopped existing. It was in every crack in the pavement, every weed in the gutter, every rat in the subway. Waiting. When we released our grip, it didn't return. It simply expanded, filling the space we vacated, doing what it was always going to do given the opportunity. So there's no ceremony because there's nothing to celebrate. Nature doesn't celebrate. It doesn't mark occasions. It just continues, eternal and patient, exactly as it always has, as it always will, until the sun grows too hot and the oceans boil away and life itself ends on this planet. Until that distant day, measured in billions of years, nature continues. With us, without us, after us. It makes no difference. The planet spins. The sun shines. Life persists. That's all. That's everything. Earth's spirit, if we can call it that, if planets can be said to have spirits, remains unchanged. The planet that existed before we built cities is the same planet that exists now, that will exist after every trace of our cities has dissolved. Same rock spinning through space. Same water cycling from ocean to sky to land and back. Same energy from the sun driving photosynthesis, evaporation, and weather. Same tectonic forces building mountains and opening oceans. Same life evolving and adapting and dying and being replaced. We changed the surface temporarily. We moved some materials around. We altered some chemical concentrations. But we didn't change Earth in any fundamental way. We couldn't. We weren't powerful enough. No single species is. Earth remains what it has always been. A dynamic, complex system, mostly water, some rock, a thin film of life, all of it heated by a star, spinning through an indifferent cosmos. Our presence was a footnote in its story, and our absence is equally unremarkable. The planet doesn't miss us. It never knew we were here in any sense that matters. It simply continues, unaware and unchanged in spirit, doing what planets do. Our cities were never destroyed. Destruction implies violence, implies an agent actively working to unmake something. That's not what happened. Our cities were absorbed, taken apart molecule by molecule, incorporated into Earth systems, digested, metabolized, recycled. The concrete became soil and became rock. The steel became rust and became mineral deposits. The glass became sand and became sandstone. The organic materials rotted, feeding microbes and fungi, their nutrients cycling into plants, into animals, into soil, around and around. Nothing was destroyed because nothing actually ends. The atoms persist, indestructible. Only their arrangements change. The city was one arrangement. The forest is another. Both are temporary patterns in the endless dance of matter. We think of death as ending, but it's really just rearrangement. The city doesn't die. It transforms, becomes something else, and that something else transforms again, and so on forever until the heat death of the universe. In this sense, our cities are immortal. They still exist, just not as cities. They exist as iron in a tree's leaves, calcium in a deer's bones, silicon in a river's sand. Every atom that was once part of a skyscraper is still somewhere, still part of Earth, still participating in the planet's endless recycling. The form called city is gone, but the substance persists. Absorption, not destruction. Transformation, not ending. Perhaps in some distant future, when our cities have become legends even to the rock layers, when they exist only as the faintest statistical anomalies in mineral distributions, perhaps then they achieve a kind of mythological status. Not myths in the sense of stories, because no one is telling stories about them, but myths in the sense of archetypes, patterns that influence the landscape in ways that persist long after the cause is forgotten. A region where forests grow unusually dense because the soil is enriched by ancient urban ruins. No one knows why the forests there are different, but the difference persists, and the forests become known as special, blessed, magical to any future intelligence that encounters them. A chain of lakes that follows the course of an ancient highway, each lake formed behind a collapsed overpass or in a subsided section of roadbed. They form a pattern, too regular to be entirely natural, and future geographers puzzle over them, giving them names that reflect their mystery. The cities become myths written in the land itself, stories told in topography and vegetation, tales that can be read by anyone who knows how to look, even though the original authors are long forgotten. In the longest view, cities affect Earth's albedo, its reflectiveness. Concrete and asphalt are darker than many natural surfaces, absorbing more sunlight. During the urban era, city locations were slightly warmer than surrounding areas. As vegetation reclaims these areas, the albedo changes. Green forests reflect light differently than gray concrete. After 10,000 years, former city locations have albedos that match surrounding natural areas. But the ruins beneath can still have subtle effects. Dark rubble under thin soil absorbs more heat than solid bedrock would. This creates microclimatic variations that persist for hundreds of thousands of years, until erosion and burial finally eliminate the effect. After 1,000,000 years, the albedo variations are gone, averaged out across the landscape, too small to detect. Earth's reflectiveness returns to what it would have been without cities, and another trace vanishes. Deep underground, in the most stable vaults we built, sealed chambers might preserve pockets of air from the urban era. Mines, deep bunkers, subterranean storage facilities, any void that was sealed and remained sealed could trap the atmosphere. After 1,000,000 years, these pockets persist, tiny capsules of ancient air. The composition is slightly different from current atmosphere. More carbon dioxide, trace pollutants, isotopic ratios that reflect industrial activity. If ever discovered and analyzed, these air pockets would be like ice cores, preserving a sample of Earth's atmosphere from a specific period. They would provide direct evidence of atmospheric composition during the urban era, undeniable proof that something unusual happened during this time period. But undiscovered, they're just voids, pockets of stale air, meaningful to no one, affecting nothing. And eventually, over tens of millions of years, even these sealed chambers breach. The rock shifts, cracks develop, the ancient air mixes with the modern atmosphere and is lost. The reservoirs we built to store water might persist for millions of years, depending on the durability of their dams. These artificial lakes become ancient features of the landscape, as permanent as any natural lake. Animals evolve strategies around these water sources. During dry seasons, herds gather. During wet seasons, they disperse. The presence of reliable water shapes migration patterns, territory sizes, population distributions. After 10 million years, the dams finally fail, and the lakes drain. But the species that evolved depending on those lakes face a crisis. Their strategies, refined over millions of years, suddenly don't work. Some populations adapt, finding new water sources. Others decline or go extinct. The reservoirs shaped evolution for millions of years, then disappeared, leaving the species they influenced to cope with their sudden absence. It's a delayed effect of human engineering, rippling forward through time, affecting life millions of years after the engineers themselves vanished. For a time, tens of thousands of years perhaps, the tallest ruins of our cities remain as vertical structures. Before they finally collapse, they serve as landmarks visible from great distances. Migratory birds, navigating by visual landmarks, incorporate these ruins into their mental maps. Generation after generation, birds learn from their parents. Turn at the tall standing structure, follow the river beyond it. After the structures collapse, the behavior persists for a while, birds still making turns at locations where landmarks used to stand. But gradually, without reinforcement, the behavior fades. New landmarks are learned. The old mental maps are forgotten. But for thousands of years, the ghost of skyscrapers guided migrating birds, shaping their routes, affecting which populations mingled and which remained separate, subtly influencing the genetic structure of bird populations across continents. Long after cities are buried, their ruins affect how fire moves through forests growing above them. Rubble piles create barriers that slow fire spread. Areas where buildings created compacted soil support different vegetation, some more fire-prone than others. After 100,000 years, fire ecologists, if they existed, might notice patterns. Fires in certain regions follow unusual paths, burning around rather than through specific areas, or burning more intensely in others. The patterns correlate with ancient urban sites. Fire has memory, in a sense, because it responds to fuel loads and moisture patterns that reflect long-buried structures. The cities shape fire behavior for hundreds of thousands of years, protecting or exposing forests through their invisible influence on the conditions fire needs. Eventually, enough soil accumulates, enough erosion occurs, that the effect disappears. But for most of 1 million years, the ghost of cities could be seen in the patterns of forest fires, written in charcoal and ash. The heat island cities created, those domes of warmth produced by concentrated energy use and heat-absorbing materials, dissipate quickly after we vanish. Within decades, the temperature anomalies are gone. But the heat we generated, the countless terawatts we produced by burning fuels and running machinery, that energy didn't disappear. It dissipated, spreading out, warming the atmosphere minutely, the oceans imperceptibly, radiating eventually into space. After 10,000 years, every joule of energy we ever produced has been distributed evenly through Earth's systems and lost to space. The planet's energy budget shows no trace of our brief period of intense energy use. It's as if it never happened. Heat, like sound, preserves nothing. It spreads and dissipates and is gone. The warmth of cities becomes the warmth of the world, becomes the cold of space, and nothing remains but the slight increase in entropy, the subtle shift toward disorder that is the true price of all our activity. In the final analysis, after 200 million years, after the continents have rearranged themselves and the species that exist are entirely different from those that existed in our time, what's left? Geological clues, subtle and sparse. Unusual sediment layers with strange chemistry. Isotopic anomalies. Possibly some durable artifacts if we're extremely lucky. That's all. A future geologist, alien or evolved terrestrial studying Earth's history, would note these clues. They'd realize something unusual happened during a brief period. An intelligent species, clearly. Industrial civilization, obviously. Cities, probably. But details? Mostly speculation. How we lived, what we valued, what our cities looked like, how we organized ourselves, what we hoped and feared and dreamed. All of this is lost completely. The geological record can't preserve such things. It can only note that something was here, that it processed materials in unusual ways, that it altered the environment briefly, and then it was gone. Our entire civilization, in all its complexity and diversity and achievement, reduced to a few anomalous sediment layers. That's the legacy. That's what survives into deep time. Not memory, not understanding, not even ruins. Just clues, bare and minimal, suggesting we existed without really explaining what we were. And finally, there is eternity. Not eternity in the infinite sense, because nothing is truly infinite, not even time. But eternity in the human sense, time spans so vast they might as well be infinite, lengths of time that dwarf our existence so completely that we become less than insignificant. In this eternity, our cities are a passing breath. A brief exhalation. The planet breathes in and we exist, builds cities, fills them with life and activity. The planet breathes out and the cities are gone, dissolved, forgotten, as if they were never more substantial than morning mist. Eternity doesn't judge. It doesn't value one thing over another. It treats everything with the same patient dissolution. Mountains, cities, species, oceans, continents, all are temporary to eternity. All will pass. All will be forgotten. All will become something else. We built cities thinking they were permanent, or at least hoping they might be. But nothing is permanent. Nothing can be. The universe itself isn't permanent. In the deepest time, even atoms decay. Even space expands until all structure dissolves. Our cities were never going to last forever. Nothing lasts forever, and in a strange way, that's comforting. It means we're not alone in our impermanence. Everything shares this fate. The mountain and the city, the species and the star, all of us temporary, all of us destined to become something else, all of us equal before the patient work of time. So the cities sink back into nature over millions of years, over hundreds of millions of years, slowly, inevitably, completely. Not because they were destroyed, but because nothing stays the same forever. Change is the only constant. Transformation is the only truth. And when the last trace finally vanishes, when Earth has fully digested the cities and incorporated them into its ongoing processes, nothing really ends. The atoms persist. The energy has merely changed form. The story continues, different now, but still the same story it's always been. Life on a planet, evolving and adapting, under a star that will eventually die, in a universe that will eventually grow cold and dark. In this story, our cities are one sentence. An interesting sentence, perhaps, but only one among billions. And when the story is read by whatever consciousness might eventually read it, if any consciousness ever does, our sentence will be noted, briefly considered, and then the reader will move on to the next sentence, the next chapter, the next era. Because the story doesn't end with us. It never ends. It just continues on and on, transformation after transformation, until the final heat death of everything. And in that continuation, in that endless becoming, there is something beautiful. Not tragic, not sad, just beautiful. The universe, endlessly creative, endlessly transforming, never stopping, never resting, always moving forward into new forms, new patterns, new possibilities. Our cities were part of that, for a moment, and now nature continues doing what it always does, being what it always is, creating the next moment, and the next, and the next, forever and ever, without memory, without regret, without anything except the pure, simple, eternal act of continuing. And perhaps that's enough. Perhaps that's everything. To have existed, to have been part of the story, even briefly, to have participated in the universe's endless creativity, even for just a moment, to have been real, to have mattered to ourselves, even if not to eternity. The cities are gone, but they were here, and for the brief time they stood, they were full of life and meaning and purpose. That time has passed, but it was real. It happened, and nothing can change that, not even the patient work of millions of years. We were here, we built cities, and then we were gone, and the cities sank back into the earth, and life continued as it always does, as it always will. That's the story. That's all the story there is. And somehow, in its simplicity, in its inevitability, in its absolute lack of sentiment or regret, it's perfect. The earth turns, the sun shines, life persists, time flows, everything changes, everything continues, and that's enough. That's everything.